In the vast, quiet expanse between the stars, objects drift silently, carrying the remnants of countless stellar systems. Among these wayward travelers, few demand our attention, and fewer still compel a re-evaluation of our understanding of cosmic mechanics. On July 1st, 2025, astronomers detected one such interstellar wanderer, an object now designated 3I Atlas, whose sheer scale defies expectation. It glides through the solar system with a subtlety that belies its immense mass, a drifting behemoth that challenges the very frameworks we have constructed to comprehend the motion and evolution of celestial debris. At a minimum estimated mass of 33 trillion kilograms, it surpasses familiar terrestrial benchmarks. The Empire State Building, for instance, weighs scarcely a fraction of this cosmic titan, yet here it moves without an audible note, producing faint gas jets while its trajectory remains nearly unaffected. The discovery of 3I Atlas does not merely expand the catalogue of interstellar visitors, it stretches the boundaries of what astronomers had considered possible. Previous interstellar objects, such as Oumuamua and 2I Borisov, were modest in scale, measurable in kilometers, but remaining within the predictable patterns of cometary physics. By contrast, 3I Atlas exhibits the paradox of massive inertia combined with active sublimation. Ice and volatile compounds escape its surface in visible jets, yet the object resists the recoil forces that should accompany such outgassing. It behaves like a freight train powered by flickering candlelight, an incongruity that invites both scientific scrutiny and philosophical reflection. This interstellar newcomer appears as a quiet giant against the backdrop of space, its nucleus potentially 5 kilometers in diameter, composed of ancient material frozen in the void of a distant star system. Its presence is a reminder of the galactic vastness and the scale of cosmic evolution that continues beyond the boundaries of human observation. Each measurement, each spectral signature, suggests layers of complexity, a chemical composition enriched in carbon dioxide, water, ice, and exotic compounds that hint at origins far colder and more distant than the familiar territories of our own solar neighborhood. Astronomers now face an uneasy question. How could such a massive object remain undetected until now, while smaller, presumably more numerous interstellar fragments escaped notice? 3I Atlas is not merely a curiosity. It represents a challenge to assumptions, a probe into the limitations of our survey techniques, and a silent teacher offering clues about the structure and dynamics of interstellar space. Its discovery prompts a reconsideration of population models, of the processes that eject planetary debris into the galaxy, and of the survival rates of objects traversing millions of light-years. Each parameter, from mass to velocity, from chemical signature to morphological feature, signals a riddle woven into the fabric of cosmic order. The visual imagery alone is haunting. Observers describe a teardrop-shaped cocoon enveloped in a forward-glowing anti-tail, a subtle defiance of the intuitive physics that guide solar system comets. Hubble, Gemini, and other observatories capture fleeting snapshots, each one layering nuance onto the emerging narrative. The object's calm, deliberate glide belies the profound scientific implications it carries, a cosmic heavyweight, a silent messenger, and an interstellar anomaly that compels the scientific community to pause and reflect. It is in these first glimpses, before detailed analysis or theoretical speculation, that the true weight of 3I Atlas becomes apparent not in tons alone, but in the intellectual and philosophical challenge it poses. This is the threshold of discovery. The stage is set for an investigation that will traverse observational precision, theoretical modeling, and speculative inquiry. 3I Atlas has emerged not merely as a data point, but as a narrative spine around which centuries of cosmic understanding may be reconsidered. Its existence invites us to contemplate the hidden architecture of the galaxy, the mechanisms by which massive interstellar debris travels unnoticed, and the subtle interplay between observation and theory that defines modern astronomy. It whispers to us through the language of mass, motion, and light, offering both a mystery and a promise that the universe is larger, stranger, and more intricately constructed than our current models can fully describe. The story of 3I Atlas begins not in theoretical speculation, but in the precise, methodical observations conducted at a modest observatory perched in the Chilean Andes. On July 1, 2025, the ATLAS facility, Asteroid Terrestrial Impact Last Alert System, recorded the first indications of an object moving along a hyperbolic trajectory that would ultimately reveal its interstellar origin. The initial detection appeared as a faint, fast-moving point of light, unremarkable at first glance, yet possessing subtle characteristics that distinguished it from the predictable motions of solar system bodies. Early algorithms, designed to filter asteroid candidates from routine sky surveys, flagged the object for closer inspection. Its trajectory, slightly inclined and unusually rapid, hinted at a visitor from beyond the gravitational embrace of the Sunday. The discovery process illustrates the quiet orchestration of modern astronomy. Automated detection pipelines identify potential objects, immediately cross-referencing positional data with extensive databases of known minor planets. Images are automatically subtracted from archival sky surveys, and differences are highlighted, revealing the movement of the unknown against a stable stellar backdrop. This meticulous method allowed astronomers to verify that the object had no prior record and was not a misclassified satellite or mundane comet. Within hours, follow-up observations commenced, drawing on an international network of facilities capable of confirming its motion. These rapid responses exemplify the remarkable coordination of contemporary astronomical practice, transforming a single detection into a global campaign of observation and analysis. Designation followed swiftly. The Minor Planet Center catalogued the object as C2025N1, yet the moniker that would enter popular usage was simpler 3I Atlas, the third confirmed interstellar interloper in human history. The 3I underscores the rarity of such discoveries. Before this, only Oumuamua in 2017 and 2I, Borisov in 2019, had traversed the inner solar system from beyond. The context is critical. Interstellar objects are not common, and each carries within its trajectory, composition, and morphology a narrative about the birthplaces and evolution of other stellar systems. 3. Atlas's detection was therefore both a technical achievement and a cosmic milestone. Observers noted that the initial visual magnitude was faint, yet consistent with a nucleus, potentially several kilometers across. Early measurements of apparent motion indicated a trajectory approaching the ecliptic plane at a shallow angle, a factor that made subsequent observation more feasible. Ground-based observatories spanning both hemispheres mobilized, providing critical time series data. Each observatory, from the southern latitudes of Chile to northern sites in Hawaii and Europe, contributed high-precision astrometry, capturing the object's right ascension and declination with sub-arcsecond accuracy. These measurements, later compiled, allowed astronomers to confirm a hyperbolic orbit incompatible with objects bound by the Sun's gravity, a signature of true interstellar provenance. Archival imagery played an unexpected but decisive role. By combing through previous observations of the same sky region, astronomers located pre-discovery images, extending the known observational arc backward by several weeks. This retrospective detection refined the orbital parameters, establishing with increasing confidence that 3I Atlas would not merely skim the solar system temporarily, but follow a defined, high-velocity path from a distant star system. Each image, each pixel of recorded light, became part of a cosmic puzzle, providing evidence not just of motion, but of composition and activity. In these early days, even before spectroscopy or detailed photometry, the presence of faint outgassing was noted. Small jets of gas and dust hinted at the physical processes that would soon become central to the object's mystery. These subtle signs indicated that 3I Atlas was active in ways reminiscent of comets, yet its scale and mass suggested a departure from familiar norms. The juxtaposition of observable activity against the backdrop of a hyperbolic, high-mass trajectory set the stage for the cascade of questions that would define its scientific narrative. How massive was it? What composition did it carry? And, fundamentally, how had it survived ejection from its home system to arrive, virtually unscathed, at our observational doorstep? Thus, the Chilean detection marks the pivotal opening act, a solitary point of light, recorded by precise instrumentation, transforms into a global enigma. It is here, in the high deserts under clear skies, that humanity first glimpsed a cosmic heavyweight whose subtle motion would belie its true mass and whose trajectory would challenge assumptions about interstellar population statistics. 3I Atlas had entered both our solar system and the record books, setting in motion a sequence of observations, analyses, and speculations that would ripple through the astronomical community. Once 3I Atlas had been confirmed as an interstellar visitor, the focus shifted rapidly from mere detection to quantifying its physical properties. Among these, the most striking revelation was the object's extraordinary mass. Preliminary calculations, derived from 4,022 positional measurements spanning 227 observatories worldwide, indicated a minimum mass of roughly 33 trillion kilograms, a scale that dwarfs all previously observed interstellar objects. To contextualize this, consider that the Empire State Building weighs only about 330,000 tons. 3I Atlas outweighs it by a factor of 40,000, moving gracefully through space, yet with no detectable change in trajectory from the outgassing expected to accompany a comet of its activity. The sheer scale is staggering, and the implication is clear. We are witnessing a class of interstellar debris previously unobserved, a silent giant that challenges our assumptions about the frequency and size distribution of such objects. The derivation of this mass estimate hinges upon an intricate understanding of cometary physics and momentum conservation. Typically, active comets develop jets as ices sublimate under solar heating, producing a measurable non-gravitational acceleration. For smaller comets, this recoil effect is easily detectable. The momentum carried away by escaping gases imparts a slight but measurable nudge to the parent body, altering its orbit. 3I Atlas, however, exhibited substantial outgassing, evidenced by visible water vapor, carbon dioxide, and carbon monoxide emissions, yet astrometric data revealed a near-zero orbital response. Applying the physics of momentum conservation, the only plausible explanation is that the object's mass is sufficiently large to absorb the force of escaping gases without detectable acceleration, yielding the astonishing estimate of tens of billions of tons. This mass places 3I Atlas far outside the parameter space of known interstellar visitors. Oumuamua, the first interstellar object discovered in 2017, possessed a mass estimated in the millions of tons, elongated and thin, showing small non-gravitational accelerations despite minimal visible outgassing. 2I Borisov, observed in 2019, behaved more like familiar solar system comets, with a roughly 1 kilometer nucleus and predictable activity. By contrast, 3I Atlas combines a massive, multi-kilometer nucleus with active sublimation, a combination that defies the previously established correlations between comet mass and observed recoil. It occupies a previously unexplored region of parameter space, large, active, and resilient. The implications extend beyond sheer numbers. Population models suggest that smaller interstellar objects should dominate in number and should have been detected before such a heavyweight. Their ejection from planetary systems requires less energy, and they are statistically more likely to drift into our observational reach. Yet, 3I Atlas arrives first, an unexpected anomaly that forces astrophysicists to reconsider either observational biases, survival probabilities of smaller debris, or perhaps the efficiency of ejection mechanisms for massive objects. It prompts the unsettling possibility that our survey data, however sophisticated, may be missing a substantial portion of interstellar matter, skewing our understanding of the galactic debris environment. Mass also informs composition and structural hypotheses. With a nucleus potentially 5 kilometers across and a density assumed to be around 500 kilograms per cubic meter, the sheer bulk suggests a gravitationally coherent structure capable of resisting disintegration over interstellar distances. Its ability to survive ejection from a parent system, transit the galaxy, and approach the inner solar system without fragmentation challenges models of material durability in the harsh environment of interstellar space, where cosmic rays, thermal cycling, and collisional interactions threaten to erode smaller bodies. 3I Atlas demonstrates that massive objects can survive these conditions, implying that the interstellar medium may harbor a class of long-lived, substantial debris previously overlooked. The discovery of such mass does more than astonish. It forces a recalibration of physical intuition. Objects of this scale, with active outgassing yet negligible recoil, push the boundaries of observational astronomy, requiring precise astrometry and sophisticated modeling to quantify. Researchers are compelled to reconcile visible activity with dynamics, to analyze dust-to-gas ratios, and to understand chemical composition in the context of momentum transfer. Each measurement, each spectral signature, is scrutinized, revealing a silent giant that defies conventional classification, at once cometary in appearance and massive beyond prior expectation. In the scientific community, the reaction is a mix of awe and cautious skepticism. Extraordinary claims demand rigorous verification, and the mass estimate, though compelling, remains subject to refinement. Yet even preliminary calculations convey an unmistakable message. The galactic population of interstellar objects is more complex than previously appreciated, capable of producing massive, long-lived bodies that traverse light years with minimal detectable response to internal activity. 3I Atlas is not merely a visitor, it is a paradigm, challenging entity, a living counterexample to simplified models of interstellar debris, and a harbinger of the discoveries that will follow as survey capabilities continue to advance. One of the most confounding aspects of 3I Atlas is the discrepancy between visible activity and the negligible orbital response to outgassing, a phenomenon often described as the rocket effect in cometary physics. In conventional comets, sublimating ices produce jets of gas and dust that act like miniature thrusters, imparting momentum to the nucleus and subtly altering its trajectory over time. These accelerations, though small, are measurable with high-precision astrometry and form a predictable relationship between mass, outgassing rate, and resulting orbital deviations. 3I Atlas, however, violates this pattern in an unprecedented manner. Despite clear evidence of outgassing including water vapor, carbon dioxide, and carbon monoxide, the object's trajectory remains indistinguishable from pure gravitational motion. Precision measurements place the non-gravitational acceleration below roughly 15 meters per day squared, effectively imperceptible against the backdrop of Newtonian forces. This paradox immediately implicates mass as the dominant explanatory factor. In order for visible gas emission to produce minimal orbital deviation, the nucleus must be extraordinarily massive. Conceptually, this can be illustrated by imagining a person attempting to move a freight train by throwing tennis balls. The balls carry momentum, yet the train remains unshaken, indifferent to each individual impact. Similarly, the jets from 3I Atlas's sublimating ices fail to impart noticeable acceleration because the body itself is so substantial. Early modeling, integrating estimated outflow rates of approximately 150 kilograms per second with measured gas velocities near 440 meters per second, converges on a lower limit of 5 kilometers for the nucleus diameter, yielding a mass on the order of tens of billions of tons. The puzzle deepens when compared with previous interstellar visitors. Oumuamua exhibited measurable non-gravitational acceleration without any visible outgassing, an anomaly that sparked theories involving hydrogen ice or elongated geometry. In contrast, 2I Borisov displayed conventional behavior, a roughly 1 kilometer nucleus with water and carbon monoxide emission lines consistent with standard cometary dynamics. 3I Atlas, however, occupies a distinct category, simultaneously massive, chemically active, and yet resistant to the expected physical consequences of its own exhalations. This places it squarely in a new regime of interstellar physics, one in which traditional assumptions about size, activity, and acceleration break down. Observational data across multiple facilities reinforces the robustness of this conclusion. Ground-based telescopes spanning continents contributed thousands of positional measurements, while space-based assets like the James Webb Space Telescope provided spectroscopic data detailing gas composition and emission rates. The integration of this dataset allows for precise calculation of the expected recoil from outgassing. Despite extensive cross-checks and error analysis, the observed acceleration remains virtually non-existent, leaving mass as the most plausible, and indeed the only credible, explanation. Beyond the immediate numerical calculations, the minimal rocket effect challenges the conceptual framework used to interpret cometary activity. Historically, the relationship between outgassing and orbital perturbation has served as a diagnostic tool for estimating mass, nucleus size, and internal structure. 3I Atlas subverts this diagnostic by demonstrating that a body can sustain substantial sublimation while maintaining an almost perfectly inertial path. This raises deeper questions about the distribution of interstellar object masses, the efficiency of gas expulsion relative to nucleus inertia, and whether other massive but unobserved interstellar bodies exist, silently traversing the galaxy. From a philosophical standpoint, the puzzle embodies the tension between observation and expectation, highlighting the limits of extrapolation from known phenomena. It forces astronomers to reconcile familiar principles with an object that simultaneously conforms and defies them. The minimal rocket effect is not simply an anomaly. It is a prompt for re-examining assumptions about the mechanics of interstellar travel, the resilience of massive nuclei, and the potential diversity of objects drifting between stars. Each observation, each spectral line, each arcsecond of measured position contributes to a growing narrative. 3I Atlas is a silent, massive traveler whose subtle defiance of physics invites reflection on the vast, uncharted diversity of the cosmos. As 3I Atlas continued its approach into the inner solar system, high-resolution imaging from the Hubble Space Telescope provided the first glimpse of its extraordinary morphology. On July 21, 2025, Hubble captured an image that immediately arrested the attention of astronomers. The object appeared enveloped in a teardrop-shaped cocoon, a compact, luminous coma surrounding the nucleus, with a pronounced forward-facing glow directed toward the sunday. Unlike most comets, whose tails are shaped by the outward pressure of solar radiation and the solar wind, this anti-solar or sunward feature seemed to defy conventional expectations, producing an optical impression of material moving against the anticipated direction of force. The image suggested complex interactions between dust, gas, and radiation, setting the stage for deeper investigation into the physics underlying its unusual appearance. The sunward glow, or forward scattering effect, is subtle yet significant. Dust particles in the coma scatter sunlight, preferentially in the forward direction, producing an apparent brightness enhancement toward the sun from the observer's vantage point. This optical phenomenon alone does not violate physics, but the combination of morphology, intensity, and persistence distinguishes 3I Atlas from familiar cometary forms. Hubble's image revealed a concentrated central brightness, indicative of active sublimation, yet the shape of the surrounding coma suggested that the dust and gas were not dispersing uniformly. Rather, the configuration implied a directional dependence, potentially arising from anisotropic jetting or variable particle sizes within the coma. Observers noted that the overall structure resembled a teardrop, with the point trailing behind the nucleus along its orbital path, while the broader base glowed forward, an alignment that creates a striking visual paradox. Subsequent observations suggested that the morphology evolved dynamically over time. The forward-directed anti-tail did not dissipate rapidly. It persisted through multiple imaging sessions, indicating that it was not merely an artifact of perspective or a transient outflow. Instead, it represented a real physical process in which the interplay between sublimating ices, entrained dust, and radiation pressure produced a structure both coherent and evolving. Modeling efforts incorporating grain size distribution, radiation pressure coefficients, and jet orientation suggested that forward scattering by larger particles, combined with continuous sublimation along specific surface regions, could reproduce the observed teardrop shape. Yet, the phenomenon remained at the edge of known cometary behavior, demonstrating the delicate balance of forces at play and the sensitivity of observed morphology to relatively small variations in physical parameters. The teardrop cocoon also provided critical clues about the object's mass and activity. Its compact, luminous nature implied a substantial concentration of material close to the nucleus, consistent with outflow rates estimated from spectroscopic measurements. Despite the visible activity, the expected non-gravitational acceleration remained negligible, reinforcing the silent giant hypothesis. The object's mass is sufficient to absorb the momentum from outgassing without perturbing its trajectory. The Hubble images, therefore, function not only as a visual marvel, but also as a diagnostic tool, linking morphology to physical parameters, sublimation dynamics, and momentum transfer. Beyond the immediate scientific interpretation, Hubble's teardrop image carries a subtle philosophical resonance. Observers are confronted with an object that is at once familiar, a comet, complete with a glowing coma and directional jets, and profoundly alien, exhibiting morphology that stretches intuition and challenges assumptions. The teardrop cocoon, luminous and ethereal, embodies the paradox of 3I Atlas. Massive, yet seemingly delicate. Active, yet indifferent to its own emissions. Visually captivating, yet dynamically enigmatic. It is a celestial icon of anomaly, a single frame that conveys both physical reality and the aesthetic depth of interstellar exploration. As astronomers analyzed the teardrop cocoon, additional questions emerged. How does the particle distribution within the coma influence momentum transfer? To what extent do sublimation patterns align with thermal gradients on the nucleus? Could the forward-directed brightness suggest previously unrecognized mechanisms of dust and gas transport? Or novel compositional effects? Hubble's observations provided the first answers in a chain of inquiry that would span multiple observatories and instruments, yet they also left the scientific community with an acute sense of wonder. The object, already massive and active, now revealed itself to be visually and dynamically complex, reinforcing the notion that 3I Atlas was more than a simple comet. It was a living laboratory in motion, a silent emissary from the stars, with lessons encoded in light, dust, and sublimating ice. Following Hubble's striking imagery, ground-based facilities provided crucial temporal context for 3I Atlas's evolving morphology. The Gemini South Telescope in Chile, with its adaptive optics and wide aperture capabilities, monitored the object continuously throughout July and August 2025. Observers noted subtle but persistent changes in the shape and orientation of the forward-directed anti-tail. While Hubble had captured a teardrop-shaped cocoon with a pronounced sunward glow, Gemini's observations revealed that this structure was not static. Over weeks, the anti-solar tail became more extended and diffuse, suggesting dynamic processes governing dust and gas release from the nucleus. These sequential images allowed astronomers to track the morphology in real time, providing a temporal dimension that Hubble's single snapshot could not offer. The evolution of the coma and tail offered critical insights into the physical processes at work. As 3I Atlas approached perihelion, the solar heating intensified, prompting sublimation of volatile compounds at varying distances from the nucleus. Water ice became active closer to the Sun, while carbon dioxide and other exotic volatiles began sublimating at greater heliocentric distances. This stratified release generated multiple jets, whose orientations and relative strengths dictated the structure of the expanding coma. Dust particles entrained within these jets followed ballistic trajectories influenced by solar radiation pressure, gravity, and local outflow vectors, resulting in the observed transformation of the anti-tail from a concentrated, forward-glowing feature into a more extended, filamentary structure. The gradual development of the tail provided a live demonstration of how physical processes on the microscopic scale, particle size, sublimation rate, and gas flow manifest in large-scale, observable morphology. Spectral imaging from Gemini further enriched this analysis. By separating light into constituent wavelengths, astronomers detected the presence of diverse volatile compounds within the coma, confirming and extending the observations made by the James Webb Space Telescope. The distribution of emission lines correlated with morphological features. Regions of enhanced brightness often coincided with elevated concentrations of water vapor or carbon dioxide. These correlations suggested that localized surface activity on the nucleus directly influenced the visible structure of the tail and coma, reinforcing the conclusion that 3I Atlas's morphology is intimately tied to its physical and chemical properties, rather than being a mere optical artifact. Importantly, the dynamic evolution of the anti-tail also had implications for orbital modeling. As the structure of the coma changed, so too did the brightness-weighted centroid, the reference point for precise astrometry. By carefully accounting for shifts in the photocenter due to evolving dust distributions, astronomers ensured that measurements of the object's position and velocity remained accurate, thereby preserving the constraints on non-gravitational acceleration. Without these corrections, changes in apparent tail morphology could be misinterpreted as motion anomalies, potentially skewing mass estimates and undermining the silent giant hypothesis. The sequential Gemini observations also illuminated the interplay between thermal effects and dust dynamics. As volatile materials sublimated, the resulting gas jets entrained dust of varying sizes, which in turn responded differently to radiation pressure. Larger grains maintained more coherent trajectories, extending the antitail in the sunward direction, while smaller particles dispersed more readily, producing a diffuse halo around the nucleus. This size-dependent behavior contributed to the gradual elongation of the antisolar tail and the emergence of secondary features, highlighting the complexity of interpreting cometary morphology at interstellar distances. From a broader perspective, the evolving appearance of 3I Atlas underscores the importance of continuous monitoring in understanding transient interstellar phenomena. While a single image can capture a moment of cosmic poetry, only a temporal sequence reveals the dynamic narrative of interaction between a nucleus and its environment. Gemini's observations bridged the gap between Hubble's snapshot and the theoretical models of sublimation, providing empirical evidence that informed simulations of gas-dust dynamics, thermal processing, and momentum transfer. In doing so, the telescope revealed not just a cometary body, but an active, evolving system whose behavior challenges preconceptions about the physics of massive interstellar travelers. Ultimately, the temporal evolution captured by Gemini highlighted a profound truth. 3I Atlas is both massive and alive in its activity, a silent giant whose subtle transformations convey volumes about its internal and surface processes. Each frame recorded the interplay of sublimation, radiation pressure, and dust dynamics, allowing astronomers to trace the invisible hand of physics acting over millions of kilometers. The object's morphology, initially puzzling and alien, became a window into the mechanics of interstellar survival, revealing the delicate balance that allows such a massive body to maintain coherence, activity, and enigmatic serenity as it journeys through the solar system. As ground-based telescopes monitored the evolving morphology of 3I Atlas, space-based spectroscopy offered an unprecedented glimpse into its chemical composition. On August 6, 2025, the James Webb Space Telescope directed its infrared spectrograph toward the interstellar visitor, detecting a rich array of volatile compounds and providing critical constraints on the physics and chemistry driving its activity. Water vapor, carbon dioxide, and carbon monoxide emerged prominently, revealing a composition atypical for objects observed at similar heliocentric distances within the solar system. The relative abundance of carbon dioxide to water, in particular, stood among the highest ever measured in a cometary body, suggesting formation in the frigid outer reaches of a distant stellar system, far beyond the carbon dioxide snow line, where temperatures remain below 125 degrees Celsius. These observations carry immediate implications for our understanding of interstellar chemistry. The presence of highly volatile species indicates that 3I Atlas's nucleus retains primordial material, largely unaltered since its formation. Unlike comets in the inner solar system, where repeated perihelion passages erode surface ices and redistribute volatile compounds, this interstellar traveler appears chemically pristine, preserving the signature of its distant birth environment. Carbon dioxide, which sublimates at far lower temperatures than water ice, dominates the outgassing profile at large distances from the Sun, contributing to the extended antisolar tail observed in Gemini and Hubble images. The spectral lines corresponding to CO and CO2 were sharp and distinct, providing precise velocity estimates for the escaping gas, and allowing the calculation of outflow rates essential for determining the object's mass. The data also indicated subtle anomalies. Minor components, such as trace hydrocarbons and organic molecules, appeared enriched relative to expectations from standard cometary formation models. These signatures point to formation conditions not replicated in the known population of solar system comets, suggesting either unusual chemical pathways in the parent system or preservation of volatile-rich regions in the nucleus, inaccessible to solar heating during previous interstellar travel. JWST's ability to probe the infrared emissions enabled the detection of these compounds at distances where visible light observations alone would be insensitive, highlighting the object's exotic chemistry and its potential to inform models of planetary system formation in other stellar environments. From a dynamical perspective, JWST spectroscopy provided essential parameters for understanding the minimal rocket effect. By measuring gas velocities near 440 meters per second and combining these with estimated outflow rates around 150 kilograms per second, researchers could calculate the expected non-gravitational acceleration. The observed acceleration, however, remained below detection thresholds, reinforcing the hypothesis that 3I Atlas possesses a mass large enough to absorb the momentum of sublimating gas without appreciable orbital deviation. The spectroscopic data thus served as a linchpin connecting observable chemical activity with the kinematic paradox that defines this silent giant. The infrared observations also offered insights into the spatial distribution of volatiles within the coma. Extended emission of carbon dioxide indicated that sublimation occurred not only from the nucleus surface, but also from icy grains embedded within the dust, contributing to the persistent forward-directed glow and the extended tail structure. This complex interplay of surface and coma sublimation challenges traditional models of cometary outgassing, emphasizing the role of particle size dependent sublimation and the influence of local thermal environments on the distribution of released gases. Philosophically, JWST's findings deepen the sense of alienness conveyed by 3I Atlas. The chemical fingerprint it carries is a testament to the diversity of conditions across the galaxy, a frozen archive of processes occurring in a distant, frigid environment beyond our direct reach. Each molecule detected is a messenger from a foreign stellar system, conveying information about temperature, composition, and formation processes billions of kilometers away. In this sense, the telescope does more than measure spectra. It reads the biography of a cosmic traveler, revealing the history of a nucleus shaped under conditions far removed from the solar system, yet now passing silently through its space. By combining infrared spectra with morphological and astrometric data, astronomers can construct a comprehensive picture of 3I Atlas, a massive, chemically complex, dynamically enigmatic object whose existence challenges models of interstellar object formation, survival, and detection. JWST's contribution is critical, offering not only chemical confirmation of the object's exotic nature, but also the empirical foundation for mass estimates, outgassing dynamics, and further theoretical modeling. It transforms 3I Atlas from a point of light into a scientifically rich entity, a silent giant with a complex interior and a story written in ice, gas, and dust, waiting to be interpreted by those equipped to read its subtle signs. As observational data accumulated, the portrait of 3I Atlas as a silent giant began to crystallize. The paradoxical combination of active sublimation and negligible non-gravitational acceleration could only be reconciled by invoking extraordinary mass. This object, producing visible jets of water vapor, carbon dioxide, and carbon monoxide, nevertheless glides along its hyperbolic trajectory as if indifferent to its own exhalations. Astronomers likened it to a freight train nudged by candlelight, a metaphor capturing both its immensity and its apparent defiance of expected cometary physics. The evidence from ground-based astrometry, Hubble and Gemini imaging, and JWST spectroscopy collectively reinforces the notion that 3I Atlas is massive enough to absorb the momentum from outgassing, confirming the silent giant characterization. The methodology underpinning this hypothesis rests on a careful synthesis of multiple data streams. Astrometric measurements from 227 observatories yielded 4,022 precise positional data points spanning May through September 2025, defining the object's trajectory with millisecond precision. Simultaneously, spectroscopic observations quantified the rate and velocity of outgassing. By combining the momentum carried away by sublimated gas with the observed absence of orbital perturbation, researchers deduced a nucleus diameter of at least 5 kilometers and a corresponding mass in the tens of billions of tons. These calculations rely on the well-established principles of conservation of momentum, and their internal consistency across independent datasets strengthens the silent giant argument. Comparisons with previous interstellar visitors accentuate the singularity of 3I Atlas. Oumuamua exhibited unexpected acceleration without visible outgassing, while 2I Borisov behaved according to classical cometary expectations. Neither offered the combination of massive size, observable sublimation, and negligible orbital response seen in 3I Atlas. It occupies an entirely new domain of parameter space, one where the physical properties of mass, composition, and activity intersect in unprecedented ways. Its presence challenges both observational assumptions and theoretical models of interstellar object populations, demonstrating that massive bodies can survive ejection, travel vast interstellar distances, and exhibit active sublimation without betraying their mass through detectable acceleration. The visual and conceptual metaphor of the silent giant serves more than poetic purpose. It frames the object within a cognitive space that integrates scale, activity, and subtlety. Observers imagine a body capable of shrugging off its own breath, an entity whose size grants immunity from the feedback forces that govern smaller comets. The metaphor captures both the measurable physics and the existential wonder of encountering such a body. It is tangible, yet anomalous, observable, yet mysterious. In essence, 3I Atlas forces a recalibration of intuition, prompting both technical and philosophical reflection on what it means to be massive in the interstellar medium. Moreover, the silent giant hypothesis carries implications for the population statistics of interstellar objects. If 3I Atlas represents a previously unrecognized class of massive debris, it raises questions about the frequency and detectability of similarly large bodies. Traditional models predict that smaller objects should be more numerous and more easily ejected from planetary systems, yet the first 3 confirmed interstellar visitors span an extraordinary range in size, from Oumuamua's millions of tons to 3I Atlas's tens of billions. The silent giant, therefore, is not merely a single anomaly. It serves as a lens through which the apparent scarcity of smaller interstellar objects can be re-examined, suggesting potential observational bias, survivorship effects, or even fundamental gaps in theoretical models. At the core, the silent giant hypothesis is a statement about the limits of knowledge and the interplay between observation, theory, and the unforeseen. It compels astronomers to integrate precise measurement with robust modeling, to reconcile the paradox of activity with inertia, and to expand the framework through which interstellar debris is understood. 3. I Atlas becomes simultaneously an empirical object of study and a conceptual challenge, a massive interstellar emissary that communicates through paradox, inviting a deeper, more nuanced understanding of the cosmos. Its silence is not emptiness, but a signal, encoded in mass, motion, and chemistry, that demands both rigorous analysis and reflective awe. To fully appreciate the magnitude and uniqueness of 3I Atlas, it is essential to situate it within the sparse catalogue of confirmed interstellar visitors. Prior to its arrival, humanity had only encountered 2 objects with a similar provenance: Oumuamua in 2017 and 2I Borisov in 2019. Each of these visitors contributed essential insights into the diversity and behavior of material traveling between stars, yet neither approached the scale or complexity now revealed by 3I Atlas. Oumuamua, with its elongated cigar-like shape and estimated mass in the millions of tons, was notable for its small size, lack of conventional cometary outgassing, and subtle non-gravitational accelerations. Its behavior inspired debate over potential cometary, asteroidal, or even exotic origins, underscoring the difficulty of characterizing interstellar debris from limited observational data. In contrast, 2I Borisov presented a more conventional profile, a roughly 1-kilometer nucleus, active sublimation of water and carbon monoxide, and an orbital path consistent with theoretical expectations for ejected cometary bodies. Borisov confirmed that interstellar objects could behave analogously to solar system comets, providing a baseline for understanding activity, composition, and dynamical response. These first 2 objects, while illuminating, occupied the lower end of the mass spectrum, reinforcing a sense of predictability in interstellar debris. 3I Atlas, however, shatters this pattern. With an estimated nucleus diameter of at least 5 kilometers and a mass orders of magnitude greater than its predecessors, it occupies a new domain in interstellar object parameter space. Its active sublimation, which produces visible jets and an evolving coma, contrasts sharply with the negligible orbital response, a combination unseen in Oumuamua or Borisov. Where previous visitors offered validation of existing cometary models, 3I Atlas challenges assumptions about the relationship between mass, activity, and acceleration. It illustrates that the interstellar medium can host massive, chemically active, yet dynamically inert bodies, a class of objects previously undetected and perhaps underrepresented in theoretical models. The comparison extends beyond dynamics to chemical composition. Whereas Borisov and most solar system comets exhibit water-dominated activity and familiar volatile ratios, 3I Atlas shows a striking enrichment in carbon dioxide relative to water, as revealed by JWST spectroscopy. This composition points to formation in a cold, distant environment far beyond the conventional snowlines associated with our solar system's comets. Its chemical fingerprint is alien yet coherent, suggesting that interstellar objects can preserve primordial material across vast temporal and spatial scales, serving as messengers of stellar environments otherwise inaccessible. The uniqueness of 3I Atlas also illuminates the limitations of previous population expectations. Planetary systems are thought to eject debris in a size-dependent manner. Smaller objects, requiring less energy to escape, should dominate interstellar space. Yet the first 3 confirmed interstellar visitors span an enormous mass range, from millions of tons to tens of billions, with the largest arriving unexpectedly first. This counterintuitive order invites reconsideration of both observational biases and theoretical models. It raises questions about survivorship during interstellar transit, Might smaller bodies erode or fragment more readily, leaving only massive, resilient objects detectable? Or does the apparent scarcity of smaller visitors simply reflect limitations in current survey coverage? Comparative analysis highlights the extraordinary nature of 3I Atlas while providing context for its scientific significance. Unlike its predecessors, it simultaneously embodies mass, activity, and chemical complexity in a way that challenges existing paradigms. By situating 3I Atlas alongside Oumuamua and Borisov, astronomers can begin to delineate the boundaries of known interstellar object behavior, recognizing both the continuity and the deviations that define this new regime. In doing so, the object becomes not merely a data point but a touchstone, prompting the scientific community to re-evaluate assumptions about interstellar debris and to anticipate discoveries that may expand this emerging category even further. Ultimately, 3I Atlas is more than a comparison to past visitors. It is a call to refine our theoretical frameworks, to embrace the diversity of interstellar phenomena, and to acknowledge that the galaxy harbors massive, active bodies whose behavior defies expectations. Its uniqueness underscores both the fragility and the resilience of current models and highlights the need for continued observation, analysis, and speculation as humanity begins to map the hidden architecture of the material bridging the stars. The precise tracking and characterization of 3I Atlas would have been impossible without the coordinated effort of a global observatory network, from northern hemisphere sites in Hawaii and Europe to southern facilities in Chile and South Africa. Over 227 observatories contributed thousands of individual measurements, collectively forming a continuous observational baseline that spanned the object's approach from May through September 2025. This distributed network enabled astronomers to record the interstellar visitor's right ascension and declination with millisecond precision, effectively transforming the Earth itself into a continent-spanning telescope capable of detecting shifts smaller than the width of a human hair when viewed from tens of kilometers away. The logistical and computational coordination involved exemplifies the modern era of collaborative astronomy, where data flows rapidly, measurements are cross-verified, and precision is paramount. Each observatory contributed positional snapshots akin to frames in a cosmic motion picture, allowing orbital analysts to trace the object's hyperbolic trajectory against the backdrop of the star field. Deviations from purely gravitational motion, so-called residuals, were examined meticulously to detect any influence of non-gravitational forces, primarily the recoil generated by sublimation. The precision of this global network was crucial. 3I Atlas exhibited minimal acceleration despite visible outgassing, and without millisecond level astrometry, these subtle discrepancies would have been undetectable. The global collaboration ensured that the silent giant's motion was characterized with unprecedented fidelity, providing both a mass estimate and confirmation of its unusual dynamics. The discovery timeline illustrates the seamless interplay between automated detection and human expertise. The Atlas facility in Chile first flagged the object on July 1, 2025. Initial observations suggested an asteroid-like body, prompting immediate follow-up by additional telescopes. Archival images, taken before the official detection, were retrieved and analyzed to extend the observational arc backward, refining orbital parameters and confirming its hyperbolic interstellar nature. Within weeks, the Minor Planet Center officially designated it as C2025N1, later popularly referred to as 3I Atlas. This rapid verification was possible only due to the coordination of observatories spanning continents and time zones, ensuring continuous coverage as the Earth's rotation brought each site into darkness and optimal viewing conditions. Beyond positional measurements, the network also enabled temporal monitoring of morphology and activity. Amateur astronomers, equipped with smaller but capable telescopes, provided valuable photometry and time series imaging that supplemented the high-resolution data from professional facilities. These contributions documented changes in brightness, coma structure, and tail evolution, providing continuous insight into the interstellar visitor's behavior. By integrating these diverse datasets, astronomers could construct a coherent, multidimensional understanding of 3I Atlas, linking its chemical composition, morphological evolution, and dynamical behavior into a unified model. The Global Observatory Network exemplifies the paradigm shift in modern astronomy. No single facility is sufficient to characterize transient interstellar phenomena. Instead, collective measurement, rapid data sharing, and meticulous cross-verification are essential for detecting subtle effects, such as the minimal rocket influence of a massive active body. This cooperative approach not only facilitated the discovery of 3I Atlas, but also ensured the reliability of subsequent analyses, from mass estimation to morphological interpretation. The object's passage through the solar system thus became a coordinated global endeavor, with every telescope acting as a node in an intercontinental web of scientific observation, capturing the silent giant's journey in unprecedented detail. The precision achieved by this network has broader implications for interstellar object science. By demonstrating that milliarc-second level measurements are feasible across multiple continents, it sets a standard for future discoveries, particularly as facilities like the Vera Rubin Observatory enter operation. The ability to detect, track, and analyze massive interstellar objects with such fidelity transforms the field, enabling scientists to test models of formation, ejection, and survival under extreme interstellar conditions. 3I Atlas, through the lens of this global network, becomes both a singular scientific curiosity and a benchmark for the collaborative, high-precision observational capabilities required to study the cosmos in motion. At the heart of understanding 3I Atlas lies a careful examination of its non-gravitational acceleration, or rather, the striking absence of it. In cometary physics, sublimation of ices produces jets of gas and dust, which act as minuscule thrusters capable of subtly nudging the nucleus from its gravitationally determined path. These accelerations are typically measurable even for distant comets and provide a critical diagnostic for estimating mass, outgassing rates, and internal structure. For 3I Atlas, however, the observed acceleration falls below the threshold of detection, measured at less than 15 meters per day squared, effectively indistinguishable from pure gravitational motion. This anomaly immediately directs attention to the mass of the object. Only a nucleus of extraordinary mass could reconcile active sublimation with negligible recoil. Calculations of the expected acceleration begin with observed outflow rates derived from JWST spectroscopy and ground-based imaging. Gas velocities around 440 meters per second, combined with outflow rates of approximately 150 kilograms per second, predict a measurable nudge under conventional cometary physics. The absence of such a response implies that the momentum from sublimating gases is absorbed by a massive nucleus, consistent with an estimated diameter of 5 kilometers and a mass on the order of tens of billions of tons. This assessment relies on conservation of momentum. The object's inertia is sufficiently large that the small forces imparted by gas jets produce an imperceptible change in velocity over the observational period. Historical context further emphasizes the anomaly. Oumuamua displayed measurable acceleration without visible outgassing, challenging expectations for a small interstellar body. Conversely, 2I Borisov behaved predictably, with a 1 kilometer nucleus and outgassing-induced acceleration in line with classical cometary models. 3 ATLAS occupies an entirely new regime, combining massive size with active outgassing and negligible orbital response. Its existence demonstrates that mass and activity can coexist in a way that produces a near-inertial trajectory, expanding the parameter space of interstellar object behavior and challenging prior assumptions about the relationship between mass, acceleration, and visible activity. Astrometric precision plays a critical role in establishing this result. Observatories across both hemispheres contributed measurements with milliarc-second accuracy, enabling the detection of deviations as small as 2/1000th of a meter per second squared. This global effort, spanning thousands of individual observations, effectively transformed Earth into a continent-spanning detector, sensitive to the minutest forces acting on an object hundreds of millions of kilometers away. The collective dataset confirmed that 3I Atlas's motion remains consistent with a purely gravitational path, reinforcing the silent giant hypothesis. The implications of this analysis extend beyond mass estimation. They suggest that our models of cometary dynamics may need refinement when applied to massive interstellar objects. The interaction between sublimating volatiles and the nucleus, the efficiency of momentum transfer, and the distribution of gas and dust within the coma all influence the observable acceleration. For 3I Atlas, the data indicate that a high-mass nucleus can sustain sublimation while remaining effectively immune to the recoil forces that would perturb smaller bodies. This finding invites a reconsideration of the diversity of physical behaviors possible among interstellar debris. Philosophically, the negligible non-gravitational acceleration underscores the paradoxical nature of 3I Atlas, visually active yet dynamically indifferent, chemically complex yet mechanically inert. The object communicates its presence not through motion, but through the subtle interplay of light, dust, and gas. It challenges astronomers to reconcile theory with observation, demanding a nuanced understanding of the balance between physical laws and the extraordinary scales that govern interstellar phenomena. In this sense, the non-gravitational acceleration or its absence is not merely a measurement, but a defining feature, marking 3I Atlas as a silent giant that compels reflection, analysis, and awe. The arrival of 3I Atlas raises profound questions about the population statistics of interstellar objects. Prior models, built upon ejection mechanisms from planetary systems and observational survey data, predicted a higher prevalence of small interstellar debris, ranging from tens of meters to a few kilometers in size. These smaller bodies, requiring less energy to escape their home systems, should statistically dominate the interstellar population, appearing more frequently within the solar system. Yet the first three confirmed interstellar visitors, Oumuamua, 2I Borisov, and now 3I Atlas, span an extraordinary mass spectrum, with the largest arriving unexpectedly, defying both intuitive expectation and predictive models. This apparent anomaly necessitates a re-evaluation of both the underlying physical assumptions and potential observational biases in the detection of such objects. One factor influencing detectability is observational selection bias. Larger interstellar objects, while rarer, present higher apparent magnitudes and are more likely to be captured in wide-field surveys, particularly those optimized for near-Earth object detection. Smaller bodies may elude detection due to faintness, rapid motion, or a combination of both, implying that current survey data underrepresents the true population of diminutive interstellar debris. Conversely, the early detection of 3I Atlas, despite its rarity, may reflect a fortuitous alignment of trajectory, activity, and observational readiness. This raises questions about whether other massive objects remain undetected, silently traversing the galaxy, waiting for the right conditions to reveal themselves. The survival of interstellar objects during transit adds another layer of complexity. Smaller bodies are more susceptible to collisional erosion, cosmic ray processing, and sublimation over the multi-million-year timescales required to traverse interstellar distances. The resilience of 3I Atlas suggests that massive nuclei possess sufficient structural integrity to survive these harsh conditions relatively intact, whereas smaller fragments may fragment or disintegrate, reducing their likelihood of detection. This survivorship bias could skew the apparent mass distribution of observable interstellar visitors, favoring the discovery of silent giants like 3I Atlas over their smaller, less resilient counterparts. The implications extend to models of galactic debris populations and ejection mechanisms. If massive interstellar bodies are more likely to survive long-distance travel, then the frequency and mass distribution of ejected material may need to be recalibrated. Traditional simulations, focusing on small debris populations, may underestimate the contribution of larger bodies, leading to gaps in our understanding of interstellar material flux. By incorporating survivorship and observational biases, astronomers can refine estimates of the interstellar population, revealing a potentially diverse spectrum that includes massive, chemically rich travelers alongside smaller, ephemeral fragments. Furthermore, 3I Atlas challenges the assumption that interstellar objects primarily originate from young, dynamically active systems. Its mass and preserved chemical composition indicate formation in a distant, cold environment, suggesting that massive interstellar objects can persist for billions of years before encountering another star system. This observation forces a re-evaluation of how material is ejected from planetary systems, the efficiency of scattering processes, and the timescales over which such objects can traverse the galaxy. The statistical rarity of massive objects like 3I Atlas may thus be a reflection not only of formation frequency but also of survival probability, highlighting the complex interplay between astrophysical processes, observational limits, and temporal scales. In sum, the population statistics puzzle underscores a fundamental tension in our understanding of interstellar debris. Theory predicts a prevalence of small bodies, yet observations reveal a more complex distribution, where massive, resilient objects may dominate detectable populations. 3I Atlas exemplifies this paradox, forcing astronomers to reconcile theoretical expectations with empirical data and prompting deeper inquiries into ejection mechanisms, survivorship biases, and the true diversity of objects drifting through the galaxy. Its presence is both a data point and a challenge, inviting reconsideration of assumptions and models in the burgeoning field of interstellar object research. Understanding how 3I Atlas reached the solar system requires an examination of the mechanisms capable of ejecting massive bodies from their parent systems. Within planetary systems, a variety of processes can impart sufficient velocity to overcome stellar gravity, allowing material to escape into interstellar space. Gravitational interactions with giant planets, particularly during the early dynamical evolution of a system, are among the most effective. Close encounters with Jupiter-sized bodies can transfer substantial kinetic energy, flinging planetesimals and icy fragments into highly eccentric or even hyperbolic trajectories. In this framework, 3I Atlas may have been a product of intense gravitational sculpting, a survivor of repeated interactions that provided both the initial impulse and the opportunity to travel vast interstellar distances. Beyond planetary scattering, stellar flybys offer another ejection mechanism. In densely populated star-forming regions, nearby stellar passages can perturb planetary systems, dislodging material through tidal forces. For smaller debris, even modest interactions are sufficient to eject material, but the persistence and trajectory of 3I Atlas suggest a more energetic or finely tuned encounter. Its mass implies that only the most extreme dynamical events could impart sufficient velocity without catastrophic fragmentation, pointing toward either a rare, close stellar encounter or a fortuitous resonance within a dynamically active planetary system. The rarity of such events aligns with the statistical anomaly of detecting a massive interstellar object as the third confirmed visitor. Protoplanetary disk instabilities also contribute to ejection possibilities. In the early stages of planetary system formation, gravitational instabilities within the protoplanetary disk can accelerate material outward, particularly in massive, gas-rich systems. Interactions between forming planets and dense disk regions can lead to the formation of spiral waves, shocks, and transient structures capable of transferring momentum to embedded planetesimals. For an object as massive as 3I Atlas, these processes alone are insufficient, but when combined with planetary scattering or stellar perturbations, they may create conditions conducive to high-velocity ejection. Modeling such complex interactions requires integrating N-body simulations with hydrodynamic disk evolution, a computationally intensive but necessary approach to reconcile observed trajectories with plausible formation scenarios. Collisional ejection within dense debris belts offers an additional, though less probable, pathway. Impacts between sizable planetesimals can transfer momentum and produce secondary fragments capable of escaping the system. However, the structural integrity of 3I Atlas, its preservation of primordial volatiles, and the absence of significant fragmentation signatures suggest that collisional ejection played a minor role in this case. Instead, a sequence of gravitational interactions, potentially spanning millions of years, likely dominated its acceleration into interstellar space, allowing it to maintain coherence and chemical integrity across the vast expanse of the galaxy. Finally, the cumulative effect of these mechanisms highlights both the rarity and significance of 3I Atlas. Its mass and composition suggest formation in a distant, cold environment, followed by ejection via a combination of planetary scattering, stellar perturbation, and perhaps disk dynamics. The complex choreography required to launch such a massive body into the interstellar medium underscores why objects of this scale are seldom observed. The detection of 3I Atlas, therefore, is not merely a matter of chance, but the convergence of extreme conditions: a massive nucleus capable of withstanding ejection, a dynamical environment providing sufficient acceleration, and the fortunate alignment with Earth-based detection capabilities. In this context, the study of ejection mechanisms extends beyond 3I Atlas itself. By understanding the processes capable of producing massive interstellar objects, astronomers gain insight into the formation and evolution of planetary systems across the galaxy. Each ejection event encodes information about the architecture, mass distribution, and dynamical history of its parent system, making interstellar objects like 3I Atlas not just transient visitors but invaluable messengers from the deep cosmic past. Their study offers a window into stellar neighborhoods that are otherwise inaccessible, providing empirical constraints on the frequency, mass distribution, and chemical composition of bodies launched into the galactic medium. The unexpected detection of 3I Atlas raises fundamental questions about survivorship and observational biases within the interstellar object population. Classical models predict that smaller bodies should dominate the flux of interstellar debris, given their relative abundance and lower energy requirements for ejection from planetary systems. Yet, the first three confirmed interstellar visitors, Oumuamua, 2I Borisov, and 3I Atlas, span a broad spectrum of sizes, with the massive 3I Atlas arriving conspicuously early in the observational record. This anomaly invites a re-evaluation of both the survival probabilities of ejected bodies and the limitations of current detection strategies. Survivorship bias is central to understanding the prevalence of large interstellar objects. Smaller fragments, while numerically abundant, face significant hazards over interstellar transit. Cosmic rays, micrometeoroid impacts, and thermal cycling can erode surfaces, fragment nuclei, or induce rotational disruption, effectively reducing the number of detectable small bodies. Massive objects like 3I Atlas, by contrast, possess sufficient structural integrity to withstand these processes, preserving both size and chemical composition across millions of years. This resilience ensures that, when detection conditions align, large bodies are disproportionately represented in the observable population, even if smaller objects vastly outnumber them in absolute terms. Observational biases further influence detection statistics. Wide-field surveys, including ATLAS, Pan-STARRS, and upcoming facilities like the Vera Rubin Observatory, are optimized for identifying objects above a certain apparent magnitude threshold. Larger interstellar objects, with greater surface area and reflective properties, are more likely to surpass this threshold, while smaller, fainter bodies may escape detection. Additionally, trajectory alignment plays a critical role. Objects passing through favorable viewing geometries are more readily captured, whereas those on less favorable paths remain undetected. The convergence of mass, brightness, and trajectory thus shapes the empirical record, potentially creating the impression that massive interstellar objects are more common than predicted, when in fact smaller bodies may simply elude observation. The chemical and morphological features of 3ATLAS also contribute to survivorship considerations. Its high carbon dioxide content and preservation of volatile ices suggest minimal thermal processing during transit, indicative of formation in a cold, outer stellar environment and long-term stability in interstellar space. The object's integrity, coupled with the silent giant phenomenon of negligible recoil, ensures that its trajectory remains coherent and predictable, enhancing detectability. Smaller fragments, susceptible to outgassing-induced rotation and disintegration, are far less likely to arrive intact at the inner solar system, further skewing the observed population toward massive, durable bodies. Taken together, survivorship and observational biases imply that the interstellar object population accessible to our instruments may differ significantly from the underlying reality. The first three confirmed visitors, though statistically rare, provide a window into the upper extremes of size and resilience. Their study informs models of ejection, interstellar transit, and detectability, suggesting that while smaller objects dominate numerically, the observable sample is weighted toward massive, structurally robust bodies. 3I Atlas exemplifies this principle. It is massive, resilient, and chemically preserved, allowing it to traverse light years unscathed and arrive at a solar system primed for detection. Its presence underscores the need for careful interpretation of population statistics, accounting for both physical survivorship and survey limitations. In doing so, astronomers can refine expectations for future discoveries, anticipate the types of objects likely to be observed, and better understand the true diversity of interstellar debris, bridging the gap between theoretical abundance and empirical observation. One of the defining characteristics of 3I Atlas, revealed through infrared spectroscopy, is its extraordinary enrichment in carbon dioxide relative to water. Unlike typical solar system comets, which exhibit water-dominated outgassing, 3I Atlas displays CO2 as the dominant volatile, a signature that points to formation in extremely cold regions of its parent stellar system. In these frigid outer zones, beyond the CO2 snowline, temperatures fall below 125 degrees Celsius, allowing carbon dioxide to condense into ice alongside other volatile compounds. This chemical fingerprint provides a window into the environmental conditions of the object's birthplace, suggesting a location far from the warmth of its host star and potentially within a protoplanetary disk rich in volatiles, yet sparse in refractory material. The dominance of carbon dioxide has both dynamical and morphological consequences. CO2 sublimates more efficiently at lower temperatures than water, driving activity at heliocentric distances where water ice remains largely inert. This outgassing contributes to the formation of the forward-directed anti-tail observed in Gemini and Hubble imaging, as CO2-driven dust particles are lofted from the nucleus and shaped by radiation pressure. The resulting tail, persistent and evolving over weeks, illustrates the interplay between sublimation, particle size distribution, and solar radiation, offering a visual testament to the influence of chemical composition on large-scale morphology. Spectroscopic analysis reveals that CO2 emission lines are concentrated in localized jets, indicating heterogeneous activity across the nucleus. Unlike smaller, water-dominated comets, which often exhibit broadly distributed outgassing, 3I Atlas demonstrates selective volatile release, with CO2 preferentially sublimating from particular surface regions. This spatial differentiation may result from variations in surface insulation, composition, or porosity, suggesting that the nucleus possesses structural complexity sufficient to sustain chemically distinct zones over interstellar timescales. Such heterogeneity is critical for modeling both the production of the anti-tail and the minimal rocket effect. Localized jets, direct gas, and entrained dust along preferred trajectories without imparting substantial net momentum to the massive nucleus. The high CO2 to water ratio also informs theories about interstellar object formation. It suggests that 3I Atlas originated in a colder, more distant environment than typical solar system comets, likely beyond the equivalent of Neptune's orbit in its host system. The presence of abundant CO and CO2 indicates minimal thermal processing over billions of years, implying that the object has preserved its primordial volatiles despite ejection and interstellar transit. Such preservation challenges assumptions about the chemical evolution of massive bodies during prolonged exposure to cosmic rays, ultraviolet radiation, and interstellar gas, demonstrating that certain objects can maintain chemical fidelity across immense spatial and temporal scales. From a comparative perspective, 3I Atlas contrasts sharply with both 2I Borisov and typical Jupiter family comets. Borisov's activity was primarily water-driven, consistent with ejection from a relatively warm system, while 3I Atlas's CO2 dominance points to colder, more distant origins. This distinction underscores the diversity of interstellar object chemistry and highlights the potential for such objects to serve as probes of formation environments across the galaxy. Each molecule, each emission line, acts as a messenger, conveying information about temperature, composition, and the physical processes operative in distant, otherwise inaccessible regions. Philosophically, the carbon dioxide-rich chemistry reinforces the alien nature of 3I Atlas. Its activity, subtle yet persistent, Its nucleus, massive yet chemically dynamic, embodies the paradoxical combination of familiarity and otherness that defines interstellar visitors. By studying these volatile abundances, scientists not only refine mass and activity estimates, but also glimpse the environmental conditions that produced this silent giant, offering a rare, empirical window into the distant, frozen reaches of the galaxy. In this chemical signature, the object tells its story of formation in the outer reaches of a stellar system, of survival across millions of years, and of a journey through interstellar space to deliver its frozen record into our observational grasp. Further spectroscopic studies of 3I Atlas revealed an unexpected chemical anomaly. Emission lines corresponding to nickel were detectable, yet the usual accompanying iron signatures were absent or significantly weaker than anticipated. In standard cosmic chemistry, nickel and iron are closely linked, often co-produced in supernova nucleosynthesis and incorporated together in planetary and cometary materials. The presence of nickel without iron in measurable quantities challenges conventional expectations, prompting questions about the formation environment and subsequent evolutionary processes that could generate such an unusual elemental ratio. The anomaly was first identified using the Very Large Telescope, VLT, in Chile, which employed high-dispersion spectroscopy to resolve fine emission features within the near-infrared and optical bands. Nickel lines, relatively weak but unambiguously present, contrasted sharply with iron's expected emissions, which were either absent or below detection thresholds. Analysts considered potential instrumental or calibration errors, but repeated observations across different nights, instruments, and wavelength ranges confirmed the persistence of the discrepancy. This phenomenon suggested a genuine chemical peculiarity within the nucleus or the surrounding coma, rather than an observational artifact. Several hypotheses emerged to explain the selective enrichment of nickel. One possibility involves primordial fractionation during the formation of 3I Atlas in a distant protoplanetary disk. In cold, outer regions of a star system, condensation temperatures for various metals differ, allowing selective incorporation of certain elements into solid phases. Nickel, with slightly lower condensation temperature than iron under specific conditions, may have been preferentially sequestered into icy grains that ultimately coalesced into the nucleus, leaving iron largely in volatile or less condensed phases. Alternatively, local chemical gradients or microenvironmental conditions within the parent disk may have promoted selective metal retention, producing a compositional signature distinct from typical solar system analogues. Another hypothesis considers photochemical and thermal processes during interstellar transit. Over millions of years, cosmic rays and ultraviolet radiation can induce surface reactions, selectively depleting more reactive or easily sputtered elements. Iron, being more susceptible to oxidation and radiative erosion, might have been partially removed from exposed surface layers, while nickel, more chemically inert under certain conditions, remained detectable in the coma. This selective sublimation or sputtering would preserve nickel emission while diminishing iron, consistent with observations. The nickel anomaly also provides insight into the physical structure of the nucleus. If nickel-rich grains are embedded within the icy matrix, their preferential release through sublimation or microjet activity could explain localized enhancements in the coma. The lack of iron emission may indicate either sequestration within the nucleus's interior or conversion into chemically bound forms that do not sublimate under solar heating. This interpretation aligns with the observed minimal rocket effect. The majority of mass, including chemically altered or refractory materials, remains inert, while trace species like nickel are selectively released without significantly perturbing the trajectory. This unexpected chemical signature emphasizes the alien nature of 3I Atlas. It suggests that the processes forming and evolving interstellar objects can produce compositions and patterns not observed in typical solar system bodies. By examining these anomalies, astronomers gain insights into the diversity of planetary system formation, the survivability of elements over interstellar distances, and the complex interactions between composition, sublimation, and observational detectability. Nickel without iron is not simply a curiosity. It is a clue, a whisper from an environment far removed from our own, preserved in ice and dust, and delivered to the solar system by a massive, silent traveler whose chemistry defies conventional expectation. The selective release of elements like nickel and the dominance of carbon dioxide in 3I Atlas's coma highlight the intricate interplay between sublimation and photochemistry. Sublimation, the direct transition of solid ice into gas under solar heating, drives cometary activity. Yet, in the case of 3I Atlas, this process occurs under extreme conditions and on a scale rarely observed. At heliocentric distances beyond 3 astronomical units, water ice remains largely inert, while carbon dioxide, carbon monoxide, and minor volatiles continue to sublimate, feeding the persistent antisolar tail. The observed chemical composition and differential element release suggest that sublimation is not uniform across the nucleus, but rather localized, controlled by both surface heterogeneity and exposure to solar irradiation. Photochemistry adds an additional layer of complexity. High-energy photons from the sun interact with surface and coma molecules, breaking chemical bonds and producing reactive species. These processes can modify both the composition and physical behavior of outgassing products. For example, nickel-bearing grains, liberated from ice matrices, may be partially ionized or excited by ultraviolet radiation, enhancing their emission lines in spectroscopy. Simultaneously, more reactive elements like iron may undergo photochemical transformation into refractory compounds that resist sublimation, contributing to their apparent absence in observational data. This dynamic interplay of radiation, sublimation, and particle chemistry produces a coma that is not merely a passive cloud of dust and gas, but an evolving, chemically complex structure that conveys the history and environmental conditions of its distant formation. The morphology of the coma and tail is directly influenced by these processes. Sublimating volatiles entrain dust particles of varying size, with heavier grains maintaining near-ballistic trajectories and contributing to the antisolar tail, while smaller particles are dispersed more broadly by radiation pressure. The forward-directed glow observed in Hubble imagery results from a combination of scattering by large dust particles and directional sublimation, controlled in part by the spatial distribution of photochemically altered grains. This explains the persistence and evolving shape of the teardrop cocoon and anti-tail over weeks of observation. Modeling these effects requires integrating thermal physics, chemical kinetics, and gas-dust dynamics. Surface temperature gradients, driven by solar insolation and rotational modulation, create regions of enhanced sublimation. Photochemical reactions further alter the physical and optical properties of ejected particles, affecting their albedo, mass, and response to radiation pressure. The resulting morphology and spectral signatures observed by JWST, Gemini, and Hubble provide empirical constraints on these models, allowing astronomers to infer not only the composition of the nucleus, but also the mechanisms governing its activity at the microscopic level. In essence, sublimation and photochemistry operate in concert to shape both the visual and dynamical behavior of 3I Atlas. The selective release of volatiles and trace metals exemplifies the nuanced chemical and physical processes occurring on the nucleus. revealing a silent giant that is both massive and chemically expressive. Each emission line, each particle trajectory, reflects a complex interaction between intrinsic properties and solar forcing, highlighting the sophistication of interstellar bodies and the challenges of interpreting their behavior from distant observations. The chemical signatures and dynamic morphology thus serve as a window into the physics of objects formed in environments far colder and more chemically distinct than the familiar inner solar system. Ultimately, understanding the sublimation and photochemistry of three Atlas bridges, observation and theory, linking the measured properties of the coma and tail to the underlying structure, composition, and history of the nucleus. These processes not only explain the object's unique spectral and morphological features, but also reinforce the silent giant hypothesis. The body's mass allows it to absorb the effects of sublimation and radiation, while still communicating its complex chemical and physical identity through the delicate patterns of outflow and photochemical modification. 3. Atlas thus emerges as a chemically and physically autonomous entity, an interstellar messenger whose subtle emissions encode the story of its formation, evolution, and enduring journey through the galaxy. The observable morphology of 3 Atlas, its teardrop cocoon, forward-directed glow, and extended anti-solar tail provides more than aesthetic intrigue. It is intrinsically linked to the underlying dynamics of the object. In comets and interstellar bodies, morphology is shaped by a complex interplay of factors: nucleus rotation, localized sublimation, gas and dust ejection, radiation pressure, and gravitational interactions with the Sunday. For 3 Atlas, these elements combine in a particularly enigmatic way. Its massive nucleus ensures minimal orbital response to outgassing, yet the morphology of the coma and tail reflects subtle momentum exchanges and chemical activity that belie the apparent dynamical inertia. High-resolution imaging reveals that jets of sublimated gas and entrained dust are highly anisotropic. Observers noted preferential emission from localized regions on the sunward hemisphere of the nucleus, creating concentrated streams of material that define the shape of the coma. These jets do not produce significant orbital acceleration because the nucleus's mass effectively dampens the reaction forces. Instead, the ejected material disperses into space, sculpted by solar radiation pressure and particle size dependent trajectories. Larger dust grains, moving almost ballistically, contribute to the coherent anti-solar tail, while smaller grains scatter sunlight, forming the diffuse halo surrounding the nucleus. The morphology, therefore, is a direct manifestation of localized activity interacting with physical forces acting on particles of varying size. Rotational dynamics further influence morphology. Even a slow rotation of the nucleus can modulate the directionality of sublimation, creating periodic changes in jet orientation and intensity. Observational sequences captured by Gemini and Hubble indicate that the coma exhibits subtle shifts consistent with rotational modulation, though the massive size of 3 Atlas mitigates any observable change in the overall trajectory. These periodic variations in morphology provide insight into the nucleus's spin rate and axis orientation, enabling astronomers to infer properties otherwise inaccessible, such as internal structure and surface heterogeneity. Morphology also interacts with solar forces. Radiation pressure acts more strongly on smaller particles, dispersing them into diffuse clouds, while gravitational forces dominate the motion of larger grains. The resulting structure, a combination of collimated jets and scattered halos, creates the teardrop-shaped cocoon observed in early Hubble images and the evolving anti-solar tail documented by Gemini. This interplay of forces illustrates that morphology is not merely a visual phenomenon, but a direct tracer of the physical and dynamical processes shaping the object. Accurate interpretation requires integrating imaging, spectroscopy, and astrometry to disentangle the contributions of mass, sublimation, particle size, and radiation. Furthermore, morphology provides constraints on sublimation rates and chemical composition. The persistence of the antisolar tail implies continuous activity over extended periods, supporting JWST's findings of CO2-dominated outgassing. Variations in brightness across the tail and coma indicate heterogeneous release of volatiles and metals, consistent with localized surface chemistry and photochemical modifications. Morphology, in essence, encodes a spatially and temporally resolved map of the nucleus's activity, offering a three-dimensional perspective on the object's physical state. The relationship between morphology and dynamics reinforces the silent giant hypothesis. Despite the visible complexity and active appearance of the coma and tail, the nucleus's massive inertia ensures that these dynamic processes do not translate into measurable changes in trajectory. This decoupling between visual activity and orbital motion is rare among comets and highlights the unique physical regime occupied by 3I Atlas. Morphology becomes both a diagnostic tool and a narrative device, revealing the underlying physics while maintaining the object's enigmatic serenity as it traverses the solar system. Ultimately, morphology versus dynamics illustrates a fundamental principle in interstellar object science. What is visible does not always equate to dynamical consequence. In 3I Atlas, the teardrop cocoon and evolving tail serve as a visual record of chemical, thermal, and mechanical processes occurring at the nucleus surface, while the massive body beneath remains impervious to these subtle forces. The object communicates through patterns of light and dust rather than motion, inviting astronomers to decode its story by linking morphology to the underlying physics, a task both challenging and revealing in equal measure. The appearance and interpretation of 3I Atlas's morphology are profoundly influenced by observational geometry, the orientation of the object relative to Earth, the Sun, and the observer's instruments. From our vantage point, subtle changes in viewing angle can dramatically alter the perceived shape, brightness, and apparent motion of the coma and antisolar tail. Forward scattering of sunlight by dust particles, for example, enhances brightness when observed near the sun's line of sight, producing the teardrop-shaped glow captured by Hubble. Variations in phase angle, the angle between the sun, the object, and the observer, modulate this effect, causing temporal changes in apparent luminosity, even if the physical outgassing remains constant. The evolving perspective provided by Earth's motion and the object's trajectory further complicates interpretation. As 3I Atlas traverses the inner solar system, observers experience changing parallax, modifying the projected orientation of jets and tails. Features that appear elongated or aligned from one observatory's perspective may appear compressed or foreshortened from another. These shifts require careful geometric modeling to ensure that apparent variations in morphology are not misattributed to intrinsic changes in activity or structure. Astrometric corrections and three-dimensional reconstructions become essential tools for disentangling observational artifacts from genuine physical phenomena. Radiation scattering properties also interact with geometry. Larger particles in the coma scatter light preferentially forward, enhancing brightness when observed along certain lines of sight. Conversely, smaller grains scatter isotropically, producing diffuse halos that are less sensitive to viewing angle. The combination of particle size distribution and line-of-sight effects results in a morphology that is highly dynamic from the observer's perspective, even in the absence of physical changes at the nucleus. Models incorporating Mie-scattering theory and particle size-dependent phase functions allow astronomers to predict these geometric effects and adjust interpretations of brightness and structure accordingly. Geometric effects also influence spectral analysis. Observed line intensities can vary with phase angle due to anisotropic scattering and absorption, affecting inferred abundances of volatiles and trace metals. Nickel emission lines, for example, may appear enhanced or diminished, depending on the orientation of jets relative to the observer, necessitating careful calibration against geometric considerations. Failure to account for these effects could lead to misestimation of compositional ratios, misinterpretation of active regions, or errors in derived outgassing rates. Moreover, observational geometry affects detection sensitivity. Certain alignments favor visibility in survey instruments, while others may render even a massive object like 3I Atlas effectively invisible against the stellar background. This geometric dependence partially explains why smaller objects remain underrepresented in detection statistics. Their faintness combined with unfavorable viewing angles reduces the probability of early identification. In contrast, 3I Atlas, massive and active, benefited from an alignment that maximized both apparent brightness and resolvable structure, facilitating rapid recognition by Atlas and subsequent follow-up by Hubble, Gemini, and JWST. Recognizing the impact of observational geometry is essential for reconstructing the true physical and dynamical state of 3I Atlas. By integrating measurements from multiple observatories at different locations and times, astronomers can correct for geometric distortions, producing accurate three-dimensional models of the coma, jets, and tail. These reconstructions allow separation of intrinsic activity from perspective effects, clarifying the relationship between observed morphology, underlying sublimation processes, and the silent giant's massive, minimally perturbed trajectory. Ultimately, observational geometry illustrates a broader principle in interstellar object science. Appearances are context-dependent. For 3I Atlas, the teardrop cocoon, the evolving antisolar tail, and the subtle brightness variations are all shaped by the interplay between physical processes and viewing perspective. By carefully modeling geometry, astronomers can extract the underlying reality from the illusions of angle and alignment, revealing the true behavior of this enigmatic interstellar visitor. The unusual combination of 3I Atlas's massive size, chemically rich composition, negligible non-gravitational acceleration, and distinctive morphology naturally invites speculation beyond traditional cometry paradigms. Among the more provocative ideas is the technological hypothesis, the notion that the object could, in principle, be artificial or modified rather than entirely natural. While mainstream science approaches this cautiously, the anomalous properties demand consideration of all possibilities, however improbable, to rigorously test conventional assumptions and constrain alternative interpretations. Proponents of the hypothesis note several features that diverge from expectations based on classical cometry behavior. First, the silent giant phenomenon, the negligible response to substantial sublimation, exceeds typical mass-based explanations for known cometary nuclei. Second, the selective release of nickel without corresponding iron is chemically unusual, suggesting either exotic formation environments or engineered modification of material. Third, the coherent antisolar tail and persistent forward-scattering glow appear finely tuned in structure, maintaining shape over weeks despite solar radiation and thermal effects. While each feature individually could be explained within natural parameters, their combined presentation is sufficiently extraordinary to warrant careful consideration of alternative frameworks. Scientific evaluation of such a hypothesis emphasizes falsifiability and empirical constraints. Any credible artificial origin model must account for the observed mass, chemical composition, and dynamic behavior without invoking phenomena that violate physical laws. Current observations, including high-resolution spectroscopy, precise astrometry, and multi-wavelength imaging, constrain properties such as density, outgassing rates, and orbital parameters, effectively bounding the range of plausible non-natural explanations. For instance, any hypothetical propulsion or structural system must operate within the limits imposed by the observed absence of measurable acceleration and the chemical activity recorded in the coma. Historical precedent informs this consideration. Oumuamua's unusual acceleration and elongated shape prompted a brief but careful discussion of artificiality in scientific literature, though natural explanations such as radiation pressure on thin, planar structures remain widely accepted. In the case of 3I Atlas, the scale of the object and its active, chemically complex coma favor natural interpretations. The immense mass alone renders artificial origin less plausible, as constructing or deploying a multi-kilometer body capable of surviving interstellar transit would require engineering capacities far beyond known technology. Nonetheless, the scientific community treats such possibilities as thought experiments, useful for rigorously testing assumptions and ensuring that anomalous observations are not prematurely dismissed. Even if the technological hypothesis is ultimately rejected, its consideration provides valuable insights. By exploring extreme scenarios, astronomers refine models of interstellar object formation, outgassing dynamics, and observational limitations. It forces critical examination of the assumptions underlying mass estimates, compositional interpretations, and the evaluation of anomalous chemical signatures. The exercise also highlights the necessity of multidisciplinary approaches, integrating astrophysics, planetary science, and chemistry to construct robust, falsifiable models capable of accounting for 3I Atlas's full range of observed properties. Philosophically, entertaining the technological hypothesis underscores the profound strangeness of 3I Atlas. The silent giant is at once massive, chemically distinct, morphologically complex, and dynamically anomalous, inviting contemplation of scenarios that challenge conventional frameworks. While natural explanations, planetary scattering, ejection from cold protoplanetary regions, survival across interstellar distances remain overwhelmingly favored, the hypothesis functions as a narrative lens, emphasizing the object's alien nature and the necessity of open-minded yet rigorous scientific inquiry. In conclusion, 3I Atlas's characteristics make it a compelling subject for exploring the boundaries of interstellar object science. The technological hypothesis, while improbable, encourages careful scrutiny of the object's mass, chemistry, dynamics, and morphology. By testing the limits of natural explanations against extreme scenarios, scientists gain a deeper understanding of interstellar processes, refining both observational strategies and theoretical models. The silent giant, whether natural or hypothetical in part, challenges astronomers to reconcile the extraordinary with the empirically constrained, illuminating the richness and complexity of objects traversing the vastness between stars. The unique trajectory and scale of 3I Atlas have prompted discussion of potential mission concepts aimed at close-range investigation, with Jupiter emerging as a feasible gravitational assist point for intercept opportunities. As the object passes through the inner solar system, mission planners consider leveraging Jupiter's gravity to redirect spacecraft toward the interstellar visitor, minimizing propellant requirements while allowing detailed in-situ measurements. Such a mission, though technically daunting, offers the unprecedented prospect of probing a massive, chemically rich, and dynamically enigmatic interstellar body at close range, providing empirical data far beyond the reach of telescopic observations. Mission design begins with trajectory analysis. Precise astrometry from 227 observatories, combined with orbital refinement from space-based imaging, establishes the window during which a spacecraft could feasibly intercept 3I Atlas. Calculations must account for the object's hyperbolic velocity, its minimal non-gravitational acceleration, and the influence of solar radiation pressure on both spacecraft and target. Jupiter's massive gravity can be employed to accelerate the spacecraft and adjust its trajectory, offering a natural slingshot that reduces travel time and fuel expenditure. Simulations suggest that an intercept mission would require precise launch timing and alignment, with small margins for error given the interstellar object's high speed and massive inertia. The scientific objectives of such a mission are compelling. Close-range instrumentation could directly measure the nucleus's mass, rotation, and surface heterogeneity, providing definitive constraints on the silent giant hypothesis. Spectrometers could analyze elemental and isotopic abundances with higher resolution than ground-based or space telescopes, confirming the unusual nickel-to-iron ratios, CO2 dominance, and presence of trace organics. Imaging systems could capture fine-scale jet structures, coma dynamics, and particle ejection patterns, elucidating the interplay between sublimation, photochemistry, and morphology. These measurements would directly inform models of interstellar object formation, chemical preservation, and survivorship across interstellar distances. Technological challenges are formidable. The object's velocity, combined with the distances involved, necessitates high-precision navigation, rapid data acquisition, and radiation-hardened systems capable of operating in the solar system's outer regions. Communication latency and bandwidth constraints require sophisticated onboard processing and autonomy, ensuring that critical measurements are captured even under limited telemetry conditions. Additionally, protective shielding must account for micrometeoroid impacts, as the spacecraft navigates both the interstellar debris field and the high-speed ejected particles from 3I Atlas itself. Despite these challenges, the potential scientific return justifies the conceptual effort. An intercept mission could resolve key uncertainties: the precise mass and density of the nucleus, the physical mechanisms underlying minimal rocket effect, the spatial distribution of volatiles and metals, and the microstructure of dust particles contributing to the anti-solar tail. Such data would not only refine understanding of 3I Atlas, but also inform broader models of interstellar object dynamics, formation, and chemical evolution. The mission would transform the silent giant from a remote observational target into an actively studied system, offering an intimate glimpse into a visitor from another stellar system. Beyond technical and scientific considerations, the Jupiter intercept concept embodies the aspirational dimension of human curiosity. It represents the possibility of reaching beyond Earth-based observation, physically connecting with material that has traversed light years to enter our solar neighborhood. In contemplating such a mission, scientists and engineers confront both the practicalities of interstellar exploration and the profound implications of direct engagement with a massive, chemically rich object whose existence challenges prior assumptions. The silent giant, already enigmatic from telescopic study, becomes a tangible candidate for exploration, reinforcing the interplay between observation, theory, and the aspirational reach of human ingenuity. Beyond its immediate observational intrigue, 3I Atlas inspires speculation about the broader role of massive interstellar objects in galactic evolution, particularly the concept of planet seeding. This hypothesis posits that bodies ejected from planetary systems, especially those rich in volatiles and complex compounds, can act as catalysts for planet formation in distant stellar environments. As such, objects traverse interstellar space. They carry with them not only chemical building blocks but also the structural integrity necessary to survive long-distance transit, delivering primordial material to otherwise nascent planetary systems. 3I Atlas, with its massive nucleus, CO2-dominated composition, and preserved trace metals, exemplifies a potential vector for such cosmic material transfer. The mechanics of planet seeding depend on the intersection of the object's trajectory with regions of active star and planet formation. As 3I Atlas approaches another young stellar system, gravitational capture or close passage could deposit dust, ice, and chemically rich fragments into protoplanetary disks. These contributions may accelerate core accretion processes, introducing preformed materials that supplement native dust populations. In particular, the presence of carbon dioxide, nickel, and other refractory compounds could enhance chemical diversity within the disk, potentially influencing the composition of resulting planetary bodies. Such interstellar contributions may partially account for isotopic anomalies or exotic chemical signatures observed in solar system meteorites, providing a broader context for understanding planetary formation across the galaxy. The survival of massive bodies like 3I Atlas over interstellar distances is a prerequisite for this mechanism. Smaller debris, while more numerous, is susceptible to erosion, fragmentation, and photochemical alteration, reducing the likelihood of delivering intact material to another system. By contrast, the silent giant's structural integrity, combined with its chemically preserved volatiles, ensures that it retains a substantial fraction of its primordial composition. This resilience allows it to function as a carrier of complex compounds, potentially seeding multiple systems during its galactic journey. Statistical modeling suggests that such events are rare but not negligible. The frequency of massive interstellar object ejections, coupled with their long lifetimes and slow dispersion, implies that a galaxy-spanning network of chemically rich travelers may exist, each contributing intermittently to the chemical and physical evolution of protoplanetary disks. While the probability of direct capture or significant material deposition is low for any single object, the cumulative effect over billions of years could be substantial, subtly influencing the frequency and chemical diversity of planet formation across the Milky Way. Observationally, evidence for planet seeding remains indirect. No confirmed exogenous contribution has been definitively identified within solar system bodies, though isotopic anomalies, trace element variations, and the presence of volatile-rich meteorites hint at such possibilities. 3I Atlas provides a tangible case study, offering insight into the type, scale, and composition of material capable of interstellar delivery. By analyzing its mass, chemistry, and trajectory, scientists can refine models of how similar objects might interact with other stellar systems, offering quantitative estimates of seeding efficiency and potential impact on planet formation timelines. Philosophically, the planet seeding hypothesis situates 3I Atlas within a broader cosmic narrative. Its journey, spanning light years and possibly billions of years, transforms the silent giant from a solitary interstellar traveler into a potential agent of galactic chemical exchange. Each molecule, each dust grain, carries the story of its origin and the potential to influence distant worlds. In this context, 3I Atlas is more than an observational anomaly. It becomes a participant in the ongoing cycles of planetary system evolution, linking stellar systems across space and time through the subtle, yet profound, agency of massive interstellar objects. The planet seeding hypothesis naturally intersects with classical models of planetary formation, particularly core accretion theory, which describes the gradual buildup of planetary cores through collisions and aggregation of smaller planetesimals. In traditional scenarios, local dust and ice particles within a protoplanetary disk collide and coalesce over millions of years, eventually forming solid cores capable of attracting gas envelopes in the case of giant planets. The introduction of massive interstellar objects, like 3I Atlas, into this environment could significantly influence these dynamics, effectively shortcutting certain stages of planet formation by supplying pre-formed, chemically rich building blocks. 3I Atlas exemplifies an object capable of delivering both mass and volatiles. Its nucleus, spanning several kilometers and composed of CO2, rich ice, nickel-enriched dust, and trace organics, represents a concentrated package of material that could seed a disk with elements otherwise distributed only in fine-grained dust. Upon entering a young system, tidal interactions or collisions with existing disk material could disperse fragments, augmenting local density and enhancing accretion rates. In this way, the silent giant could accelerate core formation, enabling faster growth of planetesimals and potentially influencing the ultimate architecture of planetary systems. The impact of interstellar seeding extends beyond simple mass contribution. Chemically diverse material, including rare elements like nickel without corresponding iron, introduces variability into disk composition. Such heterogeneity may lead to the formation of planets with unusual isotopic ratios, enhanced metallicity, or enriched volatile content, potentially affecting planetary differentiation, mantle composition, and surface chemistry. In essence, interstellar objects act as catalysts not just of mass accumulation, but also of chemical complexity, enriching emerging planetary systems in ways that local disk evolution alone may not achieve. Comparing core accretion with seeding highlights the complementarity of these processes. Core accretion proceeds from local aggregation under the influence of gravity, governed by disk density, turbulence, and collisional dynamics. Seeding introduces exogenous material that bypasses initial stages of assembly, injecting mass and complexity from beyond the host system. The two mechanisms are not mutually exclusive. Rather, seeding events may intermittently accelerate or perturb ongoing core accretion, creating pockets of enhanced growth or chemical diversity. In this framework, 3I Atlas represents both a natural interstellar phenomenon and a potential agent of planetary system evolution, its arrival capable of leaving lasting imprints on the structure and composition of the disk it encounters. Quantitative models of seeding effects rely on estimates of object size, mass, velocity, and composition. 3I Atlas, with its tens of billions of tons of mass and chemically distinct nucleus, offers a case study for calculating potential contributions to a young disk. Simulations incorporating impact probabilities, dispersal of material, and subsequent accretion rates suggest that even a single massive interstellar object could enhance local solid mass density by measurable amounts, altering the trajectory of core growth and potentially influencing the final planetary configuration. Such models underscore the significance of massive interstellar travelers, transforming them from observational curiosities into active participants in the galaxy's ongoing process of planet formation. Ultimately, the intersection of core accretion and seeding illuminates the broader cosmic role of objects like 3I Atlas. Its journey through interstellar space, chemical composition, and massive nucleus are not mere curiosities. They exemplify the potential for interstellar bodies to influence the formation, composition, and diversity of planetary systems far from their origin. By bridging endogenous accretion processes with exogenous material delivery, 3I Atlas and similar objects highlight the interconnectedness of stellar systems, the exchange of matter across vast distances, and the subtle yet profound forces shaping the architecture of the galaxy. The interplay between interstellar object population statistics and the potential for planetary seeding raises profound questions about the frequency and impact of massive travelers like 3I Atlas. Galactic models predict that planetary systems routinely eject material into interstellar space, but the size, distribution, chemical composition, and survival rates of these objects remain poorly constrained. While smaller debris is more abundant, it is also more susceptible to erosion, fragmentation, and sublimation over the millions of years required for interstellar transit. In contrast, massive bodies like 3I Atlas, resilient and chemically rich, are disproportionately likely to survive and contribute meaningfully to potential seeding events in distant star systems. The probability of an interstellar object intersecting a protoplanetary disk depends on multiple factors: the density of stars within the galactic neighborhood, the ejection velocities of debris, and the spatial distribution of disks around young stars. Statistical models incorporating these variables suggest that while the absolute likelihood of any single object being captured or depositing material is low, the cumulative effect across the galaxy and over billions of years is non-negligible. Massive bodies, due to their enhanced survivorship, dominate the observable and consequential fraction of interstellar debris capable of interacting with nascent planetary systems. Observational biases further influence perceived population distributions. Wide-field surveys are naturally more sensitive to larger, brighter objects, like 3I Atlas, while smaller fragments may elude detection due to faintness or unfavorable geometry. Consequently, the empirical record may over-represent massive bodies relative to the underlying true population. By understanding these biases, astronomers can calibrate models to account for unseen small bodies while recognizing that the massive, resilient objects detected, such as 3I Atlas, are likely the most significant contributors to potential planetary seeding. Chemical composition intersects critically with statistical considerations. The CO2 rich and nickel-enriched profile of 3I Atlas exemplifies the type of material that could materially influence a protoplanetary disk. Each delivery of such chemically distinct matter introduces variability in disk composition, enriching the potential diversity of emerging planetary bodies. Statistical modeling of population flux, combined with survival probabilities and chemical content, allows researchers to estimate not only the frequency of such seeding events, but also their qualitative impact on galactic planetary system evolution. Furthermore, these considerations suggest a feedback mechanism in the galactic ecology. Systems capable of ejecting massive, chemically complex objects contribute material to neighboring systems, which in turn may enhance planet formation efficiency or chemical diversity. Over cosmological timescales, this network of interstellar object exchanges could subtly influence the prevalence, composition, and architecture of planetary systems, establishing a form of chemical and material connectivity across the galaxy. In this framework, 3I Atlas is not merely an observational anomaly, but a node in a larger process of interstellar matter redistribution. By integrating population statistics with the mechanics of planetary seeding, astronomers can reconcile the apparent rarity of massive interstellar visitors with their outsized impact on potential disk enrichment. 3I Atlas exemplifies the consequences of survivorship and selection. Its sheer mass and preserved composition position it as both detectable and consequential. In studying this object, researchers gain insight not only into the dynamics of interstellar travel, but also into the subtle ways in which massive debris can shape the evolution of planetary systems, influencing mass distribution, chemical composition, and ultimately the formation of worlds across the galaxy. The arrival of 3I Atlas also raises questions about the cosmic timing of its detection. While interstellar objects are expected to traverse the galaxy continuously, their appearance within the observational reach of Earth-based surveys depends on a fortuitous alignment of trajectory, activity, and instrumentation sensitivity. The fact that 3I Atlas, a massive and chemically rich body, is detected before a proportionally larger number of smaller interstellar fragments presents a timing paradox that intertwines celestial mechanics with observational constraints. Its detection during an era of sophisticated, high-precision surveys underscores the confluence of chance, technology, and celestial dynamics. Trajectory geometry plays a crucial role in this puzzle. The object's hyperbolic path intersects the inner solar system at a shallow angle relative to the ecliptic, maximizing its apparent brightness and enabling detection by wide-field surveys such as ATLAS and Pan-STARRS. Had the trajectory been more inclined or the approach less favorable relative to Earth's position, the same massive object might have passed undetected, despite being larger and brighter than previously observed interstellar bodies. This sensitivity to alignment demonstrates that even rare, massive objects are subject to the same probabilistic constraints as smaller debris, and their detectability depends heavily on celestial timing and geometric coincidence. Survey readiness and technological advancement further influence detection probability. Only in recent decades have continuous, wide-field monitoring systems reached the sensitivity and cadence necessary to identify interstellar objects reliably. Oumuamua and 2I Borisov were discovered because of improved detection algorithms and survey coverage, despite being smaller and less active. 3I Atlas benefits similarly from these capabilities, with its discovery facilitated by automated pipelines capable of analyzing vast quantities of imaging data, flagging anomalous motion, and coordinating follow-up observations across multiple observatories. Without such systems, even a massive interstellar body might have escaped notice, emphasizing the interplay between cosmic dynamics and human technological progress. Temporal factors also intersect with the object's intrinsic activity. The visibility of 3I Atlas depends not only on size and trajectory but also on the rate of sublimation of volatiles such as CO2 and water. Its forward-directed anti-tail, teardrop cocoon, and dust emission enhance apparent brightness, improving detectability. Had the object passed during a period of reduced outgassing or increased heliocentric distance, its light curve may have fallen below detection thresholds, delaying or preventing recognition. Thus, the timing of observation coincides with peak activity, creating a rare window in which the object's properties could be characterized in detail. This cosmic timing paradox reinforces the role of serendipity in astronomical discovery. Despite the vast number of interstellar objects predicted to exist, the observable subset is constrained by alignment, activity, and technological capability. 3I Atlas's arrival illustrates the delicate interplay of these factors. A massive, chemically rich nucleus intersects Earth's observational plane at a time when surveys are sensitive enough to detect it, producing a discovery that simultaneously illuminates interstellar object dynamics and challenges prior statistical assumptions. Its detection is therefore both an empirical event and a reminder of the contingency inherent in observing the cosmos. Ultimately, The cosmic timing puzzle frames 3I Atlas as a product of chance within a deterministic framework. Its discovery results from the alignment of celestial trajectory, physical activity, and human technological readiness, offering insight into both the object itself and the processes by which we study interstellar space. It is a reminder that the universe is continuously populated with massive, chemically complex travelers, yet only a select few intersect our observational window, allowing the silent giants of the galaxy to reveal their stories across the narrow corridors of detection. The discovery of 3I Atlas underscores the need for continued and enhanced astronomical survey capabilities, particularly those designed to detect faint, fast-moving interstellar objects. Current facilities, including ATLAS and Pan-STARRS, have demonstrated their effectiveness, but the advent of next-generation observatories promises a dramatic increase in both detection rate and characterization potential. Chief among these is the Vera C. Rubin Observatory, whose wide-field, high-cadence survey strategy will revolutionize the identification of transient and moving objects across the sky, extending sensitivity to fainter magnitudes and enabling near real-time tracking of interstellar visitors. Vera Rubin's Large Synoptic Survey Telescope, LSST, will systematically image the entire visible sky every few nights, producing a continuous stream of data that allows for early detection of hyperbolic trajectories. Its large aperture, rapid survey cadence, and deep imaging capabilities will capture objects previously below the detection thresholds of existing systems. For massive bodies like 3I Atlas, LSST will enhance monitoring of morphological evolution, enabling precise astrometric measurements and continuous observation of coma and tail development. By providing a longer baseline of observations, future surveys will refine orbital models, improve mass estimates, and identify subtle non-gravitational accelerations with greater confidence. In addition to survey scale, future observational strategies will integrate multi-wavelength capabilities. Combining visible light imaging with infrared and spectroscopic observations from space-based telescopes will allow comprehensive characterization of composition, outgassing rates, and thermal properties. Such synergy is critical for understanding chemical anomalies like CO2, dominance, and selective nickel release. Integrating data streams across platforms enhances both the temporal and spectral resolution of interstellar object monitoring, enabling more accurate modeling of dynamics, morphology, and chemical evolution. The anticipated increase in detection rate also informs population statistics. Current models suggest that many massive interstellar objects may remain undetected due to trajectory, size, and brightness limitations. LSST's deep, wide, and frequent imaging will expand the observable sample, improving statistical constraints on mass distribution, chemical diversity, and ejection mechanisms. This, in turn, refines estimates of survivorship bias and the likelihood of seeding events, providing empirical data to test hypotheses about interstellar object contribution to planetary system evolution. Finally, future survey prospects extend to targeted mission planning. Early detection of interstellar objects creates windows for potential intercept missions, as discussed in the context of Jupiter-assisted trajectories. Knowing an object's path weeks or months in advance allows spacecraft to be positioned optimally, maximizing scientific return. By combining rapid detection with high-fidelity orbital modeling, future surveys enable both observational and in situ studies, bridging telescopic and exploratory methodologies. In summary, 3I Atlas serves as a catalyst for the next era of interstellar object exploration. Upcoming survey capabilities, particularly from the Rubin Observatory, promise to enhance discovery rates, extend characterization potential, and provide critical context for interpreting the dynamics, morphology, and chemistry of massive interstellar visitors. By expanding the observable sample, future surveys will deepen our understanding of survivorship, population distribution, and potential planet-seeding roles, solidifying 3I Atlas's position as a harbinger of the rich complexity that awaits systematic study in the galaxy's interstellar medium. The unprecedented combination of mass, chemical composition, and minimal non-gravitational acceleration observed in 3I Atlas presents formidable challenges for theoretical modeling. Classical cometary physics, derived largely from the behavior of solar system comets, must be extended to account for massive interstellar bodies whose size, density, and chemical heterogeneity lie outside previously established parameter spaces. Models must simultaneously reconcile orbital dynamics, sublimation physics, particle ejection, and photochemistry, integrating multi-scale processes that interact over spatial ranges from nanometer dust grains to kilometer-scale nuclei. One of the primary modeling challenges is reproducing the minimal rocket effect within a physically consistent framework. Traditional models link outgassing rates directly to non-gravitational acceleration, assuming a roughly spherical nucleus and uniform or weakly anisotropic sublimation. For 3I Atlas, however, mass estimates place the nucleus in a regime where standard momentum transfer equations produce accelerations far below detection thresholds. Models must therefore incorporate heterogeneous sublimation patterns, rotational modulation, and anisotropic jet orientation to explain how visible activity translates into negligible dynamical effect. This necessitates high-resolution simulations that couple thermal physics with gas-dust dynamics, accounting for particle size-dependent trajectories and radiation pressure interactions. Chemical modeling adds further complexity. The CO2-dominated composition and selective nickel release require simulations capable of tracking differential sublimation, photochemical alteration, and surface layer chemistry over interstellar timescales. These models must address not only production rates, but also the spatial distribution of outgassed material, as morphological features such as the teardrop cocoon and antisolar tail directly reflect these processes. Integrating chemical kinetics with macroscopic morphology remains computationally intensive, demanding both robust numerical methods and empirical validation from observational data. Population modeling poses an additional layer of challenge. Predicting the frequency and properties of massive interstellar objects requires assumptions about ejection mechanisms, survival probabilities, and observational biases. 3I Atlas's detection, despite its rarity, suggests that existing models underestimate either the production of massive debris, its survivability across interstellar distances, or the influence of observational geometry on detectability. Adjusting these models to accommodate such outliers while maintaining consistency with prior observations introduces significant uncertainty, highlighting the limits of current theoretical frameworks and the need for iterative refinement as new data emerges. Finally, integrating multi-instrument observations into cohesive models remains non-trivial. Data from Hubble, Gemini, JWST, and ground-based astrometry each provide distinct constraints on morphology, chemical composition, and orbital dynamics. Reconciling these datasets within a unified model requires careful calibration of temporal resolution, spectral sensitivity, and geometric effects. Discrepancies between instruments or observational epochs must be addressed to avoid misinterpretation of activity patterns, cometary jets, or morphological evolution. In essence, 3I Atlas challenges theoretical modeling across multiple dimensions: dynamics, chemistry, morphology, and population statistics. Its combination of mass, activity, and chemical anomaly pushes current frameworks to their limits, necessitating multi-scale, multi-physics simulations that integrate observational constraints from disparate sources. By confronting these challenges, astronomers refine models not only for 3I Atlas, but for a broader class of interstellar objects, extending predictive capability and deepening understanding of processes that govern the formation, ejection, survival, and observational appearance of massive travelers in the galaxy. Beyond its empirical and theoretical significance, 3I Atlas invites a profound philosophical contemplation of humanity's place in the cosmos. It is not merely a massive, chemically rich interstellar object. It is a messenger from a distant stellar system, a material artifact of processes that unfolded billions of years before the formation of Earth. Its journey across light years, undisturbed by the vast emptiness of interstellar space, challenges our perception of time, scale, and the persistence of matter. Observing 3I Atlas is to witness both continuity and isolation, a silent giant conveying the history of its origin, yet utterly detached from any immediate planetary system. The silent giant phenomenon emphasizes the paradox of visibility versus impact. Despite its massive size and chemical complexity, 3I Atlas traverses the solar system with little effect on planetary dynamics. Its presence is largely perceptual, recorded through the interaction of sunlight with its coma and tail, and interpreted through the ingenuity of telescopes and instruments. This evokes reflection on the nature of significance. A body can traverse the galaxy, enduring cosmic forces for eons, yet exert minimal influence on other systems. Its significance is revealed only through the lens of observation, interpretation, and reflection, highlighting the interplay between cosmic scale and human perception. Moreover, the chemical composition carbon dioxide-rich, nickel-enriched, and containing trace organics connects the object's distant origin to broader questions of galactic ecology. It embodies the potential for interstellar chemical exchange, suggesting that planetary systems are not isolated, but interconnected through the flow of material across space. In this sense, 3I Atlas serves as both a record of its formation environment and a participant in the galaxy's ongoing cycle of matter, contributing, however indirectly, to the chemical evolution of distant disks. Philosophically, this challenges notions of isolation, suggesting that the cosmos operates through subtle networks of interaction, even across seemingly empty space. The contrast between observable activity and negligible dynamical response reinforces themes of patience and humility in scientific inquiry. The silent giant does not shout its significance. It reveals itself gradually through meticulous observation, precise measurement, and careful interpretation. Its story underscores the value of attention to detail, the importance of sustained observation, and the limitations of intuition when confronted with phenomena outside prior experience. It reminds us that the universe is both stranger and more ordered than immediate appearances suggest. Finally, 3/80LAS embodies the tension between the known and the unknown. Each measurement, from mass to composition to morphological evolution, resolves aspects of its nature while simultaneously revealing further layers of complexity. It exemplifies the iterative nature of understanding. Every answer prompts deeper questions. Every observation illuminates new mysteries. In contemplating this object, humanity confronts both the vastness of the galaxy and the subtlety of the forces that shape it, cultivating a sense of wonder, curiosity, and philosophical reflection that extends beyond scientific data. 3I Atlas, the silent giant, is thus both a physical entity and a catalyst for contemplation. reminding us that the cosmos is a domain where scale, time, and complexity invite both empirical and existential inquiry. Despite extensive observations and modeling, 3I Atlas leaves numerous questions unresolved, underscoring the limits of current knowledge and the potential for future discovery. Its extreme mass, chemical anomalies, and minimal rocket effect are documented, yet fundamental uncertainties persist regarding its origin, detailed internal structure, and the broader population of interstellar objects. How did such a massive body survive ejection from its parent system without catastrophic disruption? What specific conditions produced its unusual carbon dioxide dominance and selective nickel release? These questions illustrate the challenges of extrapolating from limited data and highlight the importance of continued observation and theoretical exploration. The object's survival across interstellar distances raises additional speculative queries. Cosmic rays, micrometeoroid impacts, and thermal cycling should, over millions of years, erode smaller or less robust objects. The durability of 3I Atlas suggests either that massive bodies are inherently more resilient or that ejection and transit processes selectively favor survival of high-mass nuclei. This invites speculation about the prevalence of other massive, undetected interstellar objects and the possibility that our current observational record represents only a biased sample, highlighting both the rarity and potential significance of silent giants in the galactic population. Chemical questions remain equally compelling. The high CO2 to water ratio challenges standard models of cometary formation, suggesting origins in extremely cold regions or unusual chemical pathways. The detection of nickel without iron adds another layer of intrigue, prompting hypotheses involving primordial fractionation, surface processing, or selective photochemical modification. How representative is 3I Atlas of other interstellar bodies? Are these chemical anomalies exceptional, or do they reveal a broader spectrum of formation environments and evolutionary histories? These questions remain open, awaiting further detection and comparative analysis of additional interstellar objects. Morphological evolution also demands continued attention. The persistence of the teardrop cocoon, the forward-directed anti-tail, and evolving dust structures reveal complex interactions among sublimation, radiation pressure, and particle size. Yet models remain incomplete, constrained by assumptions about grain composition, nucleus rotation, and photochemical effects. How does the interplay of these processes scale with mass, and to what extent do they influence the observed morphology without imparting measurable acceleration? Understanding these dynamics is critical for refining theoretical models and interpreting future observations of massive interstellar bodies. Finally, 3I Atlas invites broader speculation regarding its potential role in galactic processes. Could massive interstellar objects contribute meaningfully to planetary system evolution via material seeding? What fraction of observed chemical diversity in exoplanetary systems could be traced to interstellar delivery? How might the discovery of additional massive, chemically complex interstellar travelers reshape our understanding of galactic material exchange and planetary formation? While definitive answers remain elusive, the presence of 3I Atlas encourages a holistic approach, integrating observation, theory, and speculation to expand both empirical knowledge and conceptual frameworks. In sum, the silent giant embodies the frontier of interstellar object science. Each resolved parameter mass, composition, trajectory uncovers further layers of mystery, while its unique properties challenge models and inspire contemplation. 3I Atlas stands as both a tangible object of study and a symbol of the unknown, reminding us that every answer in the cosmos may simultaneously illuminate and deepen the questions that drive human curiosity. As 3I Atlas recedes into the vastness beyond our solar system, the narrative of its presence concludes not with finality, but with a meditative pause. The silent giant, having traversed light years from its distant birthplace, leaves behind a tapestry of observations, its mass, chemistry, morphology, and trajectory etched into the collective understanding of humanity. Each measurement captured, each spectral line analyzed, conveys not merely data, but a story of survival, resilience, and cosmic connectivity. The journey of this interstellar traveler serves as a reminder of the scale and complexity of the galaxy, offering both awe and reflection on the forces shaping material across unfathomable distances. The observations that revealed its carbon dioxide-rich composition, selective release of nickel, and forward-directed anti-solar tail underscore the richness of information encoded in every facet of its existence. They invite contemplation of how matter persists and evolves across epochs, and how even the most distant stellar systems leave their signature on the objects they eject. Through the lens of human instruments, 3I Atlas becomes a bridge between the known and the unknown, connecting terrestrial understanding to the wider, dynamic processes that sculpt the galaxy. Its quiet passage emphasizes both the power of subtle forces and the patience required to discern them, reminding us that significant phenomena are often imperceptible until illuminated by careful observation. Philosophically, 3I Atlas challenges perceptions of scale, agency, and influence. Its immense mass and complex activity occurred largely unseen and unexperienced, influencing the solar system minimally, yet its detection has profoundly expanded human knowledge. It embodies a duality, simultaneously impactful in the realm of science, yet physically inconsequential on a planetary scale. This juxtaposition evokes reflection on human perspective, on the interplay between observation and significance, and on the humility required when confronting the vast and ancient mechanisms of the cosmos. The silent giant also emphasizes continuity amidst cosmic isolation. While individual stellar systems may appear discrete, the trajectories of massive interstellar objects reveal a subtle network of material exchange. Each interstellar traveler carries chemical and physical history, capable of seeding or enriching distant regions, and 3I Atlas stands as a tangible manifestation of this interconnectedness. Its journey invites reflection on the impermanence of location, the endurance of matter, and the invisible threads linking distant stellar environments. As the object fades from observational reach, the mind lingers on the narrative it leaves behind. It is a story of resilience, of survival across the void, and of the delicate balance between motion, chemistry, and time. For humanity, 3I Atlas represents both a scientific triumph and a philosophical meditation, a silent witness to the grandeur of interstellar processes, a reminder of the vastness of the galaxy, and a prompt to consider our own place within this immense and intricate cosmos. The silent giant departs, yet its impact endures, shaping knowledge, imagination, and wonder. In its quiet passage, the universe whispers a story of scale, patience, and cosmic resonance that will echo through observations, models, and reflections for years to come. As 3I Atlas drifts farther from the sun, its luminous antitail fades, and the teardrop cocoon dissipates into the interstellar void. The visible signs of its passage linger briefly in telescopic records, but the silent giant itself returns to the cold, unobserved regions of space from which it emerged. In this slow retreat, the mind of the observer can relax, allowing the intensity of empirical measurement and theoretical speculation to soften into quiet reflection. The cosmos, vast and patient, continues its motion without haste or urgency, indifferent to human timelines, yet offering glimpses of processes and phenomena that evoke both awe and humility. There is a calm in contemplating the enduring journey of this massive interstellar traveler. Its survival across light years, the preservation of volatile ices, and the persistence of chemical anomalies speak to the subtle yet persistent forces that shape matter across the galaxy. The silent giant's voyage reminds us that the universe operates on scales and timescales far beyond immediate perception, and that understanding is an ongoing process of observation, modeling, and contemplation. Each photon captured, each spectral signature analyzed, is a small thread connecting human curiosity to the larger cosmic narrative, offering insight into origins, evolution, and the intricate dance of matter in the void. In the fading light of 3I Atlas, one can sense the balance of scale and patience inherent in astronomical study. The object departs quietly, leaving no trace of disruption, yet its discovery reshapes understanding, illuminates processes, and deepens philosophical reflection. There is solace in the subtlety of its presence and the enduring lessons it imparts. We are reminded that even in silence, massive forces traverse space, carrying histories, compositions, and connections beyond immediate comprehension. The galaxy is alive with travelers like 3I Atlas, and in observing, modeling, and reflecting upon them, humanity engages with the universe's quiet grandeur, poised to receive its lessons with wonder, patience, and humility. Sweet dreams,